your yellow line.
We can't see your yellow curve. Just see the black and the blue curve exact and the
11 series
11
scalar
series
term.
solar turn, but don't
Maybe
see the.
then you can't see my second page.
Yes,
Okay,
yes,
okay,
yes.
yes.
Oh my God.
হয়তো কিন্তু
Yeah, it's coming.
but yeah,
It's
this
calling,
this
it's
this,
calling.
this.
So,
We can see the yellow curve.
Okay. So YOLO part is the two-term perturbative solution. So I have just retained two terms and I have plotted it. So it is okay. So I'm not happy with this sort of thing, and then I retain two more terms. Okay. So if you see when I just retained four terms, so the red line is the prediction from the four terms. Okay. So you see the matching. Okay, so it's like just magic. Okay, so it's just I introduced a parameter into the problem, and instead of solving it using this conventional power series solution, I try to solve it perturbatively, what I notice is it almost matches with the exact solution. Okay, so that is how this is how powerful these perturbative techniques are. Okay. So yeah, so before I go into, so it's a very toy problem I discussed. So before I move into some more complicated problem, non-trivial problems, I have to introduce some notations and definitions. Okay, so what are my notations and definitions? So these are as follows. Let's say I have two functions which are defined in some deleted delta neighborhood or deleted epsilon neighborhood of x naught. Okay, I have two functions f and g. Now f is very small compared to g, or f is little o of g as x goes to x naught. So when I say f is much smaller than g as x goes to x naught, if I see this limit x goes to x naught, f by g is 0. Okay, so I'm assuming that g doesn't vanish in the neighborhood of x naught. Okay, so that's the definition of f being little o of g. Okay, I think you all of you are aware of these definitions. Okay, so for example, if you see sin x is x plus little o of x as x goes to 0. Okay, or sin x minus x is much smaller than x at the in the vicinity of 0. Okay, several other examples. X is much smaller than 1 over x as x goes to 0. X to the power 1/2 is much smaller than x to the power 1/3 as x goes to 0 from above. And log of any power is much smaller than x to the power 1 by any large. Okay, so these are all I'm trying to say is log x also goes to infinity and x also goes to infinity, but x goes to infinity at much higher rate. Okay, so limit x goes to infinity, log x by x is 0. Okay, so I'm trying to say is in log x of very large is much smaller than x to the power very small as x goes to infinity. Okay, on the other hand, x of very large is much smaller than log x of very small as x goes to 0. All of we know about these things. Okay, so this some examples I want to explain in the context of this little o of. Then there is another definition which is asymptotic relation. I have two functions f and g. I say f is asymptotic to g as x goes to x naught if the relative error between f and g is much smaller than g. Okay, or equivalently limit x goes to x naught f by g is 1. Okay, So if limit x goes to x naught, f by g is 0, then I say f is little o of g. And if limit x goes to x naught, f by g is 1, then we see f is asymptotic to g as x goes to x naught. Okay. Example, if we have f, let's say f is x square plus x log x, then what can I say f is asymptotic to as x goes to infinity? F is asymptotic to x square, because log x is much smaller than x as x goes to infinity. On the other hand, what is fx? What is fx asymptotic to when x goes to 0? It is x log x. Okay, because log x is much higher than x as x goes to 0. Okay. Similarly, sin x is asymptotic to x as x goes to 0. Okay. So these are some examples in the context of what is the meaning of asymptotic relation. Okay. And the last the last definition which I'm going to explain is f is capital A of g. Okay. So I remember I defined f, what is the meaning of f is little o of g. Now I'm defining what is f is capital O of g or big O of g. If I see that mod of f by g is bounded by some positive constant in the deleted neighborhood of x naught, then I say that f is capital O of g, or fx is at most of order of gx as x goes to x naught. Okay. So for example, sin x is x of x plus order of x cube. For equivalently, I can write x plus order of x square. Okay. Now, there are several other examples. So if you want, I can share you this PDF. You may have a look. So the last definition is this ORDG. When I like, what is the meaning of ORDG? If I see that f is order of g and g is also capital O of f, if these things hold, then I say that f is order of g. Okay. And alternatively, limit x goes to x naught, f by g should be non-zero, then we say f is order of g. Okay. Examples, if x sin x is, well, I forgot to mention this. So x sin x is order of x when x goes to infinity. Okay, and so on. Okay. So these are some definitions which I wanted to introduce. So yeah, so maybe these definitions you have already learned in some basic textbooks of analysis. Now I define two important things, which are asymptotic series and asymptotic sequence. Okay. So all of you are aware of what is the meaning of a sequence. Okay. So now I'm defining a new sequence which is called as asymptotic sequence. I have a sequence like this. We say to form an asymptotic sequence as x goes to x naught if I see that this relation. Okay. So for example, delta 3 should be much smaller than delta 2 as x goes to x naught. Okay. So similarly, delta 4 will be much smaller than delta 3 as x goes to x naught. Okay. So this side of sequences are called asymptotic sequences. Okay. Yeah. So one example of asymptotic sequence is, that is all of we are aware about, is this powers, the sequence of powers. Okay. So it's an asymptotic series as x goes to 0. Why? Because what are the terms of the sequence? It's 1, x square, x cube, and all of us know that, let's say x square and x cube. X cube is much smaller than x square as x goes to 0. Similarly, x square is much smaller than x at x goes to 0. So all I'm trying to say is x square also goes to 0, x also goes to 0, but x square goes to 0 at very faster rate than x. So it's a trivial example. Now let me take a non-trivial example. What is that sequence? 1 x log x, x square log square x square log x square, and so on. Okay, and I am saying that it is an example of an asymptotic sequence as x goes to 0. Why? Because if you take any two members, let's say x log x and x, okay, x log x as x goes to 0 is 0, right? Log x goes to minus infinity, but because of this free factor x, it goes to 0. X log x goes to 0. X is goes to 0, but x goes to 0 at much faster rate than x log x, right? So therefore, x is much smaller than x log s in the vicinity of 0. Similarly, x square log square x is much smaller than x in the vicinity of x equal to 0. Okay, so it's an example, non-trivial example of an asymptotic sequence. Okay, and one more thing is that it's not necessarily be true that asymptotic sequence always converge. Okay, like sequence doesn't converge, it may happen that asymptotic sequence also doesn't converge. Okay, in fact, most of the practical asymptotic sequences, they don't converge. Okay, so next is asymptotic series. Okay, suppose that I have an asymptotic series as x goes to x naught, and I write, so this is some sort of representing f in terms of an asymptotic series like this. So we say that the right hand side summation n goes from 0 to infinity a n delta n x, it is an asymptotic series representation of fx, or f is asymptotic to this as x goes to x naught if I see that when I retain n number of terms, and what if left is small o of delta nx. Okay, so let's say I have retained 5 terms. Okay, so the last term is, so it starts from a0 delta 0x plus dot 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 a5 delta 5x, and then whatever it remains, so the remainder fx minus that is much smaller than delta 5x. Okay, so this is representation of f using asymptotic sequence. Okay, so this kind of series are called asymptotic series. Okay, again, if you remember when you studied series and sequences, like I write fx as a series representation as long as the series converges to fx, right? But that is not true for asymptotic series. Okay, asymptotic series we write, but it may not converge. The criteria for asymptotic series representation is that as you retain more and more terms, the next non-zero term is much smaller than the last retained term in the limit of x goes to x naught. Okay, so there is a clear difference between a series representation and an asymptotic series representation. Okay, so an example includes, let's say I have the function tan epsilon. Okay, so as epsilon goes to 0, the Taylor series expansion of tan is this, so which is of course is asymptotic series representation, and another expansion of tan x is this. Okay, so it's an example of a so the first one is power series representation, and second one is a non-trivial asymptotic series expansion. Okay, but the thing is that these are not really interesting because both of them converge. Okay, so I told you that it's not necessary that asymptotic series will converge. Okay, in fact, most of the important asymptotic series, they don't converge. Okay. So let's take this function. Okay, it's called exponential integral. So I have limit x goes to infinity to the power minus t to the power minus 1 dt, and x is positive. And let's say I want to see the asymptotic series representation of this as x goes to infinity. Okay, so yeah, So the problem is obtain an asymptotic series representation for this exponential function. And I don't have time to show you that how do I get to this line, but it is this. Okay, so it's e to the power minus x by x, and then the next correction is e to the power minus x by x square, and so on. Okay, so that's the asymptotic series representation as x goes to infinity. Okay, and it is an example of an asymptotic series which doesn't converge. Okay, so with this I end the this definitions and notations. Now let me show you some of the real problems. Okay, so the next topic which I am going to discuss is matched asymptotic expansions. Okay, so under matched asymptotic expansion, so what happens is I have a differential equation, and if you remember the first example here, there I had a single perturbative series. The perturbative series, it was like y0 plus epsilon y1x plus epsilon square y2x, and I solved it perturbatively and I got a nice match. But in matched asymptotic expansion, what happens is life is not that simple. What happens is I have several regions of the problem domain, and each of the domain I have a different asymptotic series. Okay, so the first problem I encounter here, I have two regions where I have two asymptotic series and eventually they match. Okay, so let's take an example, epsilon y double prime plus y prime plus y equals to 0, where y at 0 is 0 and y prime at 0 is 1. And let's say epsilon goes to 0 from above. So I have this sort of initial value problem. Is this initial value problem visible? Deepanjana, are you with me? Swaraj?
Yes.
Yes. So
Is it visible?
yes, it's visible. Okay.
So,
No problem.
yeah. So are you able to follow at least some part of it?
Yes. We are following.
So I have a nice second order ordinary differential equation, an initial value problem, and you see the coefficients are constant. So this initially value problem got unique solution, right, from the uniqueness theorem. Well, some of you may say that I can solve this analytically. Okay, let's for this timing, let's forget that I can solve it analytically. So forget that you can solve it analytically. And how do you solve it otherwise? Epsilon is a small parameter, and epsilon is attached with the highest order derivative. So let's naively try to solve it in this way. Let's say that that asymptotic series corresponding to y is this: y naught t plus epsilon y1 t, and so on. Just try. And what is the asymptotic sequence, corresponding asymptotic sequence? Here, 1 epsilon square. It's an asymptotic sequence as epsilon goes to 0, right? Good. Okay. So I have assumed a solution of this form. Then what does y naught satisfies? I simply substitute this side of series in the differential equation and in the initial conditions. So what does y naught satisfies? Right? So y naught satisfies the first order differential. You can just simply substitute this and check that at leading order y naught satisfies this differential equation. What is that? dy naught dt plus y naught equals to 0. And what are the conditions? Y naught at 0 is 0 and dy naught dt at 0 is, or y naught prime at 0 is 1. So you see that we have the first order ordinary differential equation, which is easily solvable. When I solve, it's like some constant times e to the power minus t. And how do I obtain those constant? From the initial or boundary condition. But here we have a scenario where I have one condition, I have one constant, but two conditions. Okay. So if you substitute y not being at 0 is 0, you get a is 0, and if you substitute this as 1, and then you get a is something else. So we are into some sort of trouble. So it's impossible to satisfy both the conditions. Okay. So we are into some sort of trouble. What is the trouble? That no matter however small epsilon is, okay, you may take epsilon to be whatever small it can be. This differential equation 1 is well posed. It has a solution, right? It has got a unique solution because we have the uniqueness is assured from the uniqueness theorem. As long as epsilon is there. But if you substitute epsilon to be 0, then we have something which is not well posed but ill posed. This system doesn't have a solution, right? This dy naught dt plus y naught equals to 0. This. So I have a scenario where when epsilon goes to 0 in that limit, I have a well posed problem. Nice. But when I substitute epsilon being 0, then the problem is ill posed. So epsilon tends to 0 is not equal to epsilon equals to 0. So what we call this kind of problems in asymptotics is singular problems. Okay. So singular problems are important and difficult. So what happens is, remember, how do I get this equation governing y naught? By neglecting this epsilon y double prime. Okay. So maybe near 0, it is not a good idea to neglect epsilon y double prime. Okay. Because the conditions are given at 0, y at 0 is 0 and y prime at 0 is 1. So if you think that it's an equation involving time, so t, let's say t being time, and maybe initially the epsilon, let's say epsilon is small mass, so maybe initially this mass times acceleration, initially near t equals to 0, maybe it is important. Okay, so maybe epsilon is very, very small, whatever small it can be. So the epsilon y double prime, that product is not of negligible magnitude. Okay, so something close to 0 is, we have something suspicious, and when I'm away from 0, then things are fine. Okay, so let's see what is happening. So close to 0, let's say, so remember this is the expansion I started with, and this expansion it breaks down near t equals to 0. Okay. So let's say I take a small interval delta t, where is this asymptotic relation is not true. Okay, we call this region is the inner region, or the problematic region is called an inner region. So why it is called inner? Because of some historical reasons. Okay, so I expect that in this inner region, this epsilon y double prime is non-negligible. Okay, so can you tell me, like, what will be the order of y in this inner region? So I'll help you. So I have taken a region of thickness delta t close to 0. And what is the order of y? I don't know, because the differential equation doesn't help me. Y at 0 is 0 doesn't help me. But I have this dy dt at 0 is 1. Okay, so it's like y by t is 1 close to 0. So if you are saying t is of order delta t, then y also has to be of order delta t. Okay. So now let's see what happens. Okay. So y is of order delta t and your t is also of order delta t. And in this inner region, what is epsilon y double prime looks like? It is epsilon and y double prime is delta t by delta t square. Eventually it is epsilon by delta t. And the next term was dy dt. So dy dt is y is delta t, t is delta t. So eventually it's order 1. And then you have delta t. Okay. Then I do something, some kind of sort of comparison, which is called dominant balance. So you remember I am close to 0. So delta t is small, right? So delta t is small. This term is 1. And what about this term? So there are many possibilities. Well, if this term, the first term is small, smaller than 1, then among these three terms, what is larger? The larger term is the middle one. So what I have is dy dt is 0, y is constant. It's not helping. So dominant and so the third term must match with the first term, right? So first of all, third term cannot match with the, sorry, the first term cannot match with the third term. So in the inner region, I'll introduce a new asymptotic expansion. Okay. So before I proceed, let me rescale it. Okay. So you remember t was order epsilon. Epsilon is very small. So I introduce a new variable t. It's a stretch variable. How do I define capital T is t over epsilon? Okay. So I apologize. I'll take 5 minutes extra. So let me explain at least this problem. Then t is epsilon capital T. Okay. And how do I define y as? Y is epsilon y. Okay. So that's how I define my new y and new time, new dependent variable and new independent variable. So if I define my new dependent and new independent variable, then the original differential equation in this inner region, it looks like this. Okay. Corresponding to these are my initial conditions. Okay. And then I solve this perturbatively, like y is y naught plus epsilon y1 in this way. So this is one approach. In second approach, what I do is I introduce a new stretch variable t, new independent stretch coordinate t, which is t over epsilon, and y remains the same, right? So this capital Y, which satisfies this sort of equation and this sort of initial condition. And instead of starting from order 1, I start from order epsilon. I start from order epsilon because of dy dt at 0 is epsilon, right? From this condition, it's actually telling us that I must start from order epsilon. So the asymptotic series doesn't start with y naught, rather epsilon y1 t plus dot 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 dot. Okay. So then the y1 satisfies this sort of differential equation and this sort of conditions. Okay. Now I can solve this because I have a second order differential equation with two conditions. Okay. I solved it, I got this. Okay. So y is this and t is t over epsilon. Okay. So if I divide my region with this blue line, so I have a linear region which is of thickness order epsilon, and there my solution is epsilon times 1 minus e to the power minus t. outer solution. Okay. So let me go back to the outer again. So outer means the original, the non-stretched region. So I start with again order epsilon. Why? Because the inner solution suggests that it should be of order epsilon. So I start with this, and then it satisfies this. Okay. Now remember, we are in the outer region, and in outer region I do not have an initial condition or a boundary condition because I am far away from zero. Outer region is far away from zero. So whatever conditions I had at zero, I have utilized it to found the inner solution. So what is the condition that will help us to determine A1? The condition is that I had an inner solution, and inner solution must match with the outer solution. Okay. So that matching condition will give me A1. Okay. So the matching condition is as follows, that as t goes to infinity, so t goes to infinity means I am going out of the inner region, t goes to infinity, capital I1 must match with as t goes to 0 plus small y1. Okay. So if you do this matching condition, then what you get is A1 is 1 and your inert solution is this. Okay. So that's what you got, the solutions in the inner region and the outer region, but at leading order. Okay. And in principle, I should calculate more terms over here. Yeah, so in principle, I should calculate this, but I don't have time to calculate this. Okay. So when you calculate this order epsilon square terms in the inner and outer region, then again you have to do some sort of matching. Okay. So I'll introduce two things, just I'll briefly tell you the names. So when I calculate these higher order terms and you try to do matching, then this sort of intuitive matching fails. That limit t goes to infinity and then small t goes to 0. This type of intuitive matching fails and it doesn't work. Okay. So for example, okay, so I don't have to tell you the example. So how do you proceed? So there are two ways, two techniques. One is using intermediate variable. So what happens in intermediate variables is you define an intermediate region where these two solutions actually overlap, and from there you get those matching conditions. And the next is very powerful, something called Van Dyke matching rule. Okay. So you can use either of them, and I don't have time to explain all of this. So basically, I have obtained terms up to order epsilon square. Okay. So the inner solution capital Y is this, up to when I calculate up to order epsilon square, and the outer solution up to order epsilon square is this. Okay. And now let me plot it. So this red line, the first red line is the solution obtained from the inner part, and this red line is solution obtained from the outer part. And believe me, I have plotted the exact numerical solution with blue curves, and the matching is so nice that that blue class is the blue line is not even visible. Okay. So the red portions have overlapped the blue ones. Okay. So that these part-additive techniques are so powerful. Okay. But the problem with this sort of problems is that you have to define this asymptotic series in several regions, and eventually they match. Okay. So now you see the last concept which I'll tell you is, you see near zero. Near zero is the inner region where I told you that epsilon y double prime is important. Although epsilon is small. So this is the region where you see the solution changes very rapidly. In a small thickness, solution changes very rapidly. Although t is small, but epsilon y double prime is of manageable magnitude. Okay, so this sort of region where the solution changes very rapidly is called a boundary layer. Okay, so many of you may be aware of the concept of boundary layer in fluid mechanics. Okay, so it's a layer near to the boundary from where the vorticity gets generated. So although it's a different story altogether, so the boundary layer is the region where solution changes very rapidly, and my naive outer solution was unable to predict the solution completely because this problem is singular and there is a boundary layer in this problem. Okay, and so with that I stop because I don't have time to explain more and more problems, and now I request all of you to ask me questions. Okay.
So dear participants, if you have any questions, so you can do.
No question.
So dear participants, if you have any questions, so you can do. Otherwise, we are running late. So, Saikat,
Yeah.
thank you for your nice presentation.
Yeah. Okay. Thank you very much for inviting me. Because of this technical glitch, otherwise I would have explained one more problem. I apologize. Because this problem is not really interesting because you can solve it analytically. But I have problems which cannot solve it analytically and which you can. For example, I wanted to explain this problem which you cannot solve analytically, but I don't have time. Anyway, thank you, Saurabh. Thank you, Dipanjana, for inviting me.
Saikat, kindly share your PDF with us.
Okay.
Okay. If
So we see you again in later second half session.
Okay. So it starts at 2, right?
Yes.
Okay.
2:10.
2:10.
Okay.
So I can contact you.
Okay. Thank you.
Okay. Thank you so much, Dr. Shah, for your insightful presentation. Your
So I may
idea.
leave now? Okay.
Okay. Thank you. Sorry, okay. It is my pleasure to introduce our second invited speaker, Dr. Soumen Kumar Dash. Dr. Dash is an accomplished researcher whose academic contributions include advanced work in mathematical modeling, numeric analysis, and emerging computational techniques. His publications and international collaboration reflect a deep commitment to mathematical innovation. The title of his talk is Integrating Public Transit into Urban Last Mile Logistic, the Taipei Metro Case Study. Thank you, Doctor, for have with us. Thank you. We are delighted to have you. Sir, you may kindly begin your presentation. Over to you, sir.
Am I audible?
Yes, you are
Okay.
audible, sir.
Okay. Let me just. Is my screen visible?
I am interacting because Sir Professor Shankar Kumar is with us. So, sir, welcome you in this session.
Thank you very much, Panjana. Thank you.
Thank you, sir. Thank you for with us. Thank you.
Okay.
Is my screen visible, sir?
It is clear, visible. You start your
Okay.
presentation right now.
Okay, thank you so much. Good afternoon, everyone, and thank you very much for the kind introductions. I would also like to thank the organizing committee for inviting me, and also my PhD supervisor and always mentor, Professor Shankar Kumar Rai. So today I will talk about our recent works, the integrating public transit into urban last mile logistics, the Taipei Metro case study. Actually, here in this study, we will discuss an extension of the classical routing problem by introducing mainly three key features. The first one is the introduction of public transit systems, the integration of parcel lockers, and the inclusion of delivery option. Lot of delivery option we can give. So these additions are motivated by the growing need for more efficient and flexible, sustainable last mile delivery in the urban areas like Taipei. Taipei is the capital of the Taiwan. Okay. So here is my outline of my talk. I will start with an introductions and background and focusing on the main challenges in the last mile delivery, how we tackle and also how we tackle the challenges by the technology. And then I will briefly then we briefly review the related work using public transport and parcel lockers in the logistics. After that, I will introduce the mathematical formulations and the solution methodology. And then we will look at the experimental design and followed by a real world case study. And then finally, I will present some sensitivities and key sites and discuss some insights and conclude with possible directions for the future research. So let's begin with the challenges first. The first challenge we see that with the rapid growth of e-commerce, urban parcel delivery volumes day by day increased sharply. So recent parcel global volume around like 170 billion in 2022, and day by day it's going strongly and expected that it should be like 27, like 50% around more than. So this leads to another problem, the road congestions, pollutions that are increasing and which contributes traffic congestions and pollutions. The urban freight is responsible for a larger portions for the traffic, city traffic, and also for the carbon emissions also, carbon dioxide also. At the same time, also we see that the public transit, like the pictures, the often underused during off-peak hours. Mainly buses, metro, and trains runs with plenty of spare capacity. Meanwhile, we also notice that some delivery fail at the first attempt. Because recipients are not at the home during the delivery time. So these challenges highlight the need for more efficient and flexible last mile solutions. So given these challenges, we explore how the technology can support the last mile delivery system. So we see that one approach maybe the use of public transit in the last mile delivery systems, because then we can use the spare capacity on metro, trams, on the trains during the off-peak hours, and that also reduce the number of vehicles in the dense area and reduce the congestions and emission also. And already we have a building structure, so it will be easy for us. Like on the top right side, we see that two pilot projects, Germany and UK already used to for the transport the parcels, but that not in the last mile. They are like after that they used cargo and vans for the delivery purpose. And also we see that in Indian Railway parcel delivery systems from very early that there are dedicated parcel coach are used to move goods from between the cities. And another motivations we can say the parcel lockers. The parcel locker is the benefit we can that there are provide 24/7 self-service pickup that avoid missed deliveries, reduce the dependency on the home pages, and which is crucial for working customers. And also the parcel lockers allow the consolidation of many parcels at a single locations, enable more efficient routing, and that can be also located with the station and the stores also, like different shops also. Here we see that on pictures that parcel lockers are already installed in the metro station in the Taiwan, and also smart parcel lockers are located at the convenience stores in the Taiwan. So building on that motivations, we have mainly three objectives. The first one, to integrate the public transport into the last mile delivery to enhance the sustainability, and to incorporate the parcel lockers to reduce the missed deliveries and offer flexible delivery options. And other one is the to calculate the total cost so that we can both regular vehicles and public transport, so that we can compare that if we use only regular vehicles, what happen, and if we use regular vehicles and public transports together. So to place our work in the context, this table summarizes the relevant research on the public transport routing related papers. Early works like Tenitin and Mahelen in 2010 and 2012. They use the concept of share passenger and brute force concept, but they only give a concept like that. We can use share passengers and flow together, not any provide mathematical formulation or something like that. So after that, most follow-up studies, such as by Gillas, Mason, focused on the pickup and delivery problems and applied a lot of methods for the solve the problems, like the heuristic, something like they use. And however, very fewer studies parcel lockers incorporate the parcel lockers. Even fewer consider delivery mode flexibility. Like Gatta is one of the few to introduce the user attributes, but still lacks a unified cost-based formulations. In this sense, we see that a few studies have explored the innovative elements such as drones, GTSP formulations, meta-heuristics, and Villa and Monjon introduced parcel lockers, while Endroven and Drone looked at capacitated vehicle routing problem, Phaetons transit separately. But despite this progress, also recent years also, Mondwell and Archetti, we see that, and Young and Song, they used the South Korea public transportation systems in recent times. Despite this progress, none of these models integrate all the aspects like the public transit, parcel lockers, flexible delivery, so that we face the challenges with a unified capacitated routing framework. So to address these gaps, our main contributions are like threefold. So what we propose here, we propose a new variant of routing problem that we call capacitated vehicle routing problem with public transit and parcel lockers. This is the short form. And developed a mathematical model that support three types of delivery options: home, self-pickup, and flexibles, and developed a hybrid LNS heuristic for the medium and large-scale instances. And then we do a lot of numerical experiments and real-world case studies so that our formulations, our proposed algorithms works well and efficiently like that. So this is our problem descriptions. To explore the use of public transportations in the last mile delivery, we consider the Type A metro systems, also known as Type A mass rapid transit, that called MRT in short. So Type A MRT. From there, we use this term Type A MRT as a representative public transit networks. The proposed CB-VRP network consists of one depot, set of regular vehicles, means these are the vehicles those carry parcels, or we can say the trucks. Set of three types of customers: home delivery, self pickup, and flexible. Home delivery customers means they only served by their home address by regular vehicles. Self pickup is collect from the parcel lockers. They can collect this anytime. Generally, we have given time period, like within 2 days or 3 days, we can collect that parcels. And the flexible customers, they can be served. They have open choice, like they can be served at home or preferred by lockers. And MRT stations equipped with lockers allowed inter-stations persons transfers via MRT. And parcel lockers, here these parcel lockers means the lockers in the MRT stations and also the outside also. So this is our network as we discussed. This the depot, This is the home delivery customers, regular vehicle directly visit here. This is the self pickup customers that attached any parcel lockers. Here, this is the parcel lockers. And this is the MRT stations starting. And this, if we say that this one is starting, so this one is ending. So the starting station, this is the ending stations, and the every starting stations and ending stations are equipped with parcel lockers. This is the parcel lockers that also attach some customers here. And this is the flexible customers. They can use these parcel lockers or directly visit by the vehicles. And so this is our network, and the vehicles will start from the depot and end in the depot. The regular vehicles are serve the home delivery customers, lockers, and MRT stations, carry the total demand. Carry the total demand and the MRT lines are used direct arc between MRT stations. They used to transfer parcel between the stations. So these our mathematical model. This is our objectives, that total operational cost. These costs include two terms. The first one is the travel cost of the regular vehicles, and second one is the outsourcing cost paid by the MRT company. And these are our constants, the flow and routing constant. I didn't write the all mathematical expressions. It's just which type of constants works here that I will mention here. So that the first, the constant 2, 3, 4, what indicates, the constant 2 indicates each customers or locker or station is visited exactly once by the regular vehicles. This is the basic structure of routing problem, that the truck should be visited at most exactly once. And vehicles starts and ends its routes at most once, and the flow conserved across the network for every vehicle. These constants are the same with the classical vehicle routing problems. This is the common with the every routing problem. Continuing with the routing constants, the next constant is the MRT station are allowed to be visited only once per route. Depot related constants ensure that vehicle departures and returns are balanced. Home delivery customer must be physically visited, whereas self pickup customers are only served through lockers, not directly. For flexible customers, the model ensures that they are served either at home or at a locker, not both. When using MRT for parcel transfers, the origin station must be visited, and the MRT arcs are only active if both origin station is visited. There actual demand and there is actual demand at the demand stations. Again, these are the scheduling constants. That 13 to 14 is track the departure times of the regular vehicles from customers and station locations. 15 ensures the capacity limit for each regular vehicles, that this vehicle can carry this type of demands. Every vehicle has a capacity that should be like, we can 1.5 ton, 2 ton, something like that. So ensure parcel lockers, the constant 16 that ensure that the parcel lockers loads. Every parcel locker has also capacity, something they can store 10 parcel or 20%, something like that. So constant 16 ensure that load transfer via MRT arcs does not exceed the MRT capacity, because we have also MRT capacity. And lastly, the constant 7 maintain the parcel locker capacity, ensure lockers are not overloaded during the delivery cycles. Together, these constants add operational relation to the model by incorporating time and the capacity limitations. And final, we have the synchronization constant, because we have to now synchronize all of these elements. So these 18 to 21 ensure that each customer is served usually exactly one methods. That is constant 8 ensure that it should be by it be home delivery, then served by their address. Constant 19 self pickup, for self pickups customers must collect from the parcels. And 20 flexible customer must select either home or locker delivery, not both. And 20 locker assignment is required for all non-home customers. And 20 to 24 define the relationship between the variables. Like a locker must be reachable by a vehicle or MRT to be assigned. Flexible customers must be visited by a vehicle if assigned home delivery. And locker assignment must match the customer's allowed preferences. So these sections, I will discuss about the solution methodology that we proposed here, hybrid adaptive large neighborhood search, short form is ALNS. This is very popular for using this type of framework, the routing problem. LNS is very popular, and here we use some modification. That's why you implement the hybrid. So hybrids means here we use some constant programming also to use that public transportation fast. So first what we did, first we initialize the solution by the greedy solution, and then each iterations we have a use destroy and repair operators. Destroy operators will destroy something, the solutions, and repair should be that repair to generate a new solution. Then we run each a local search to improve it. And then we decide whether we keep the solution or not by simulating type acceptance rules. If it is okay, otherwise, again repeat this process until we return the best solution found. So this is our framework to solving this capacited vehicle routing public transit parcel lockers problems models. And stopping criteria, we have included the 5,000 iterations here. No limit for time, but we get less time here. So this is our solution representations. This slide shows that how we represent a solutions inside the algorithm. On the left, this assigned to customers to the lockers, that which customers are assigned to which lockers and which MRTs are used. And from this, we build a sequence of stops that still need to be visited by trucks and with their aggregated demand. At the bottom, this sequence is converted into vehicle routes. Each road here is the one truck route and listed the customers it serves. On the right, we use two operators, L1 and L2. L1 operator only can change the truck's routes, but L2 operators are higher level that we call in L2. They can change the locker assignment, MRT uses, and they use more powerful repair procedures. This is our solution representation of the framework. So our model is implemented in MPL and solved by exact solver Gurobi. That the version is 12 point that versions. And hybrid LNS is coded in C++ and solved it using Visual Studio. And the experiments conducted in that workstations with their configurations. The goal is to evaluate the performance of our enriched capacited vehicle routing model, particularly under MRTs, public transit, and the parcel lockers features. So here, this slides describes how we generate the benchmark instances, because we need some instances to check our model validity. So that's why we generate some benchmark instance based on some existing benchmark. This benchmark is for the capacited vehicle routing problems. So from that, we choose the customers, the homogeneous vehicle capacity, the operating cost. So operating cost, everything we choose from their instances, but we divided the customers types, because we have a 3 type of customers. So we divided it 30% for self pickup. If total customers is 100, then 30 is self pickup, 30 is flexible, and the remaining is the home delivery customers. And for self pickup and flexible customers, locker choices are determined by the proximity. Nearby lockers they will prefer. And these slides how we include the MRT in that MRT systems in that benchmark instances. All MRT stations whose layout is fixed across the instances, and a set of external parcel lockers which are placed randomly there. And the capacity of each parcel locker we sample from 70 to 150 units. Capacity of MRT lines equals to the capacity of locker at its terminal stations, and outsourcing cost is same cost with the routing cost of the vehicles. And what we do for each scenario, each instance, we solve for each instance, we define 4 scenarios. Like for M0 means no MRT lines available. These are as traditional routing problem. And M1 is like 1 line available, M2 is 2 lines available, M3 is all 3 lines are available. And lockers And finally, we note that lockers at the MRT stations are always usable, even if the corresponding line is active or inactive. It doesn't matter. So finally, we also create some additional small-scale instances by sampling subsets of customers from these benchmark instances in 30 and keeping the depot location is unchanged. So on these slides, I summarize how we name the instances and the data sets looks like. We have two instances families. One is we directly augmented the aggregate instances, and we generated some small instances between these customers numbers, 6 to 26 customers. And the naming format like that, A is indicate the original aggregate instance, and N is the total number of customers with the depot, and XX is the number of customers. So N33 means that we have 32 customers, one depot. And Y is the number of vehicles. So how many vehicles are available there? So if we get K6, so 6 vehicles is there. And the number of available MRT lines is like M is denoted for the MRT in this index. So 3 means that 3 lines are available. And W is the number of parcel lockers. B is the index of the parcel lockers. So 7 means here 7 lockers are available. 6 are in MRT stations because we have 3 MRT lines. One just in the plot. We see in the plot 3 MRT lines, 1, 2, 3, the blue lines, MRT lines. And every MRT station has a locker. So 6 lockers are there and 1 locker is outside. So 7 lockers. So we what we did here, overall by varying these parameters like MRT lines 0 to 3, external lockers 1 to 6, customers 5 to 79, and vehicles 2 to 10, we obtain total 192 synthetic instances. Okay. And this is an example of a generated instance that how the instance set looks like that. So here is the blue is home delivery customers, red is for self pickup, and yellow is just flexible customers. They have both options. So nearby they can use by parcel locker, also the vehicles direct visit. And we will when we solve the instances, we will we will see that how the results, the solution representation of this instance set. So now I will present the results from our computational experiment, starting with the small AG instances. A means the generated small instance set. So for each instance, the table represents the Gurobi on the left side and the hybrid LNS on the right side. The cost is the routing cost. Gap is that optimality gap for Gurobi. And this gap is for the relative gap for the hybrid LNS versus Gurobi. And the CPU is the computational time. And used MRT shows that how many MRT lines are actually used. Our savings means the percentage of cost savings compared to the no MRT case. Means if we don't allow any MRT, like in the first case, there is no MRT. So if we use MRT, so how many costs are reduced there? The average cost percentage we calculated by this column. So when we see the instances, every instance we solve 4 cases that I already mentioned. M0 is no MRT available, 1, 2, 3. So when MRT is used, the cost saving is for small instance is more. And then when okay, I will describes. Okay, when these are the one MRT used, and the gap is, we see that gap is the 0. 0 means that the Gurobi provides optimal solutions. And with respect to that solution, hybrid LNS also provide the gap is 0%. Here we provide the average, mention the average. Why? That for each instance we run 10 times. So that's why after 10 times we average that cost, that gap. That's why, and CPU time also. That's why we mention here average for the hybrid LNS. Okay, when we see these instances like N6 to N9, the Gurobi provide the optimal solutions, and also the computational time is less. Next, here we provide N10 to N13. Just we see that here also Gurobi provide optimal solutions and the computational time is less, but higher than the previous instances. And same for hybrid LNS, we see that that gap is 0 and the computational time is more or less same. But when we, the next slides, these slides, when we see that the gap is still now 0% up to 16 customers, and that computational time is increases, and but in 17 customer we see that there is a gap of around 15%, and the computational time is so much. But with respect to these solutions, if we see the hybrid LNS provide the gap 0%, and also CPU time is very less. So for these small instances, we can say that hybrid LNS essentially matches the optimal Gurobi solutions, but with much shorter run times. And we already see that the cost savings is also decreases when the MRT are used. That's why we generate some small instances, because Gurobi can't solve the when the number of customers increases. Like up to 17, the Gurobi is solved with gap without no gap. This are the no gap, but this one is gap. After that, the gap. So that's why I don't provide the solution here. This is the full benchmark coverage summary that we tested for small 6 to 25, but I presented there earlier just up to 17 customers. After that, there are gaps. So that how many gaps, how many times we calculated, that I will discuss in the next slide. So this is the full benchmark coverage. Like medium for we choose 25 to 50 customers, large for 50 to 80 customers. So we have this 80, this 64, this 48, so total 192 instances. And the same comparison we also do, like Gurobi versus hybrid, and also MRT-based savings in every instance set. So this is the one example of solutions that from the benchmark set that already I already described in that instant generation slides. That how the vehicles routes find the routes, optimal routes, that minimizes the cost, also using the MRT here also. If we see the dotted solid color line, that are for the vehicle routes. This one is the depot. So one vehicle is start from here and back again here. This is the another vehicle that also visit the parcel lockers. This is the another vehicles and visit the terminal station of the MRT stations, and this is the outside parcel lockers. So one MRT used, that's why one vehicle visit the MRT station also. Here one MRT used, and this vehicle just visit the MRT stations, and here also one MRT used. So that's why these vehicles visit the MRT stations to give the parcels to the MRT company carry the parcel, and they deliver the next. They deliver the next. And from there, the self pickup or the flexible customers collect their parcels. So this summarize the computational results on the benchmark instances. So if we see hybrid LNS, for hybrid LNS, we run 10 runs per instance, and we report average cost and CPU time. And for Gurobi, we give a maximum 4-hour time limit, because otherwise it takes so much time. Sometimes we test with 8 hours, 16 hours, but still it's a gap. So we fixed 4 hours, and based on that optimum value or best bound, we calculate the relative gap performance. This is the relative gap performance formula. For small scale, you see that Gurobi average is 13%, means the gap average, but the computational time is okay, this one. But for medium, the Gurobi optimal gap is around 50%, and computation, I think near about this seconds, I think 4 hours, near about 4 hours around. And same for the large also. Here also we see that the gap is average gap is more. So when the number of customers increases, when the N is increases, the gap is more. But for LNS, if we see the gap with respect to these solutions, some also negative. These are more negative. Negative means the better solutions with that solutions, because when Gurobi provides the gaps, means that solution is not optimal. That is the suboptimal solutions. So with that respect to the solutions, the hybrid LNS provides better results also, and that when the N increases, it's more negative. And some cases they have a little bit bad results, but with very less computational times. That our motto, that we want to propose an heuristics that we solve large-scale instances, very lower computational times, and the gap also with respect to the Gurobi is the gap also we can and the gap in the gap also better also in some cases for large instances. So this is of the effect of MRT lines on cost and mileage. The summarize that this slide summarize how adding MRT lines affects cost and vehicle mileage. If we add if we want 2, 3 lines available, if we add more lines, how should be the gap? How should be the cost average reduced on that instances, and what about the vehicle mileage? So if we see that on the left, that the cost average savings compared to the baselines without MRT lines for small instances, we get about 17, 21. When one MRT lines used, 17, two MRT lines used, I think 21% around, and when 3 MRT lines are used, around 23%. So percent savings. For medium instances, the savings around 3, 4, and 6%. And for large instance are only about 3-4%, and for 1-2 lines, and somewhere it didn't use that 3-line scenarios also. And this is the right hand plot. We see that corresponding vehicle mileage savings also, similar patterns. So overall, we can see that as we add more MRT lines, more parcel can be shifted to the public transport while reduce the operating cost and driving time. And for some large instances, however, the spatial layout, sometimes what happens, the customers and lockers are already close to the stations, or depot is far from the MRT station, and sometimes home delivery customer is near about the MRT station. So that time the vehicle should be visited there because home delivery customers only be delivered by the regular vehicle, not by the MRTs, the public transports. That's why sometimes on the large instances the effect of MRT is not so much. But one thing we can say that when MRT lines or public transport uses, the cost is decreases, vehicle mileage is also decreases from that. So this, now I will move to the real world case study based on the Taipei metro systems. Here actually Taipei has, I think, now 6 to 7 MRT lines, but here we use 3 main MRT lines because these are main 3 lines. The one is red, one is green, and one is blue. So we call red, green, blue. So we work with 3 main MRT lines and add parcel lockers into 2 ways. Some lockers that are already installed in the MRT stations, that some lockers in the MRT stations, and some locker we placed in the outside. That in our convenience stores, there is 7-Eleven convenience stores, they have locker facility. So we use that lockers here. All coordinates for the terminals, lockers, buildings in Taipei City and New Taipei City from the OpenStreetMap via Overpass API. And depot we coordinate close to the city centers, middle something like here we put the depot. Okay, I think here we put the depot. Okay, so depot is located closely to the city center, and home delivery customers are sampled from the commercial residential building, while still pickup and flexible customers are chosen, so that at least one locker is within about the 5 kilometers, and the distance matrix is based on the actual distance here. The diving distance, actual diving distance, all points from the OpenStreetMap. So here we denote the T for the Taipei instance. Other is same style. N101 means 100 customers, 1 depot. K3 means 3 vehicles are available. N3 means 3 available MRT lines are available, and B17 means that the lockers. Some 6 are already in MRT stations, and 10 are outside the 7-Eleven stores. And these are the key parameters that here we choose 200 units, the vehicle capacity, and the cost is 25 NTD per kilometers. For the trucks, 1.5 to 2 tons payload. And for MRT outsourcing, we use this data for MRT metro Taipei system. For the red lines means the starting and end stations, they have a fare, but for use the parcel, here we discount, I think we use the 50% discounts of that price. So if the near about 64 or 65, so use 50% discount, because generally for delivery the parcels always take less amount. With that assumptions, we use this price. This is the vehicle the MRT capacity for the red line. This is the green line. This is the blue lines, and the inbuilt locker capacity is there. And the external locker capacity we choose from 20 to 60 units randomly. And this is the results from the hybrid LNS, because from the benchmark instances, we decided that LNS provides very good results with respect to Gurobi and with less computational time. So here all results are solved by the hybrid LNS, and this is for the small cases 11, 21, 41s, and this is the routing cost. This is the CPU time. CPU time is very less. I think this is 63, around 65 seconds. Use MRT in small instances, it use 1, 2, 3. When you use 3, more savings in every instance set. And for medium, we use 51, 6 means 50 customers, 60 customers, 80 customers. And same pattern we follow. When they use the MRT more, lines more, then the cost is more. And similar for the large instance set also. Finally, these are the for large type instances with 101, 151, and 201 customers. Again, we compare with M0, M3, and we see that MRT is still used, but the additional savings are relatively small, often around 1 to 10%, and in few scenarios even slightly negative. So this is the overall effect of MRT lines on type A instances. Same pattern we follow for the benchmark instances. We aggregate these results by network size. This for less than 40 customers, this 40 to 80 customers, this is for greater than 80 customers. So we see that when you use more MRT lines, the cost savings is more, and same for the mileage savings also. I think for small network, up to 30% cost savings, 50% mileage savings, and medium is large, that also. That is our main target. If we reduce the mileage savings, the driving time, that should be reduce the congestion, traffic congestion, also as well as the pollution also in the urban city logistics. So in these slides, we discuss the sensitivity of the system if we varies the MRT cost. So these are on the x-axis. This is the percentage. This is the actual price, and this is the discount. This is the cheaper. So means 20% if we 20% cheaper, 40% cheaper, and 60% cheaper, and if this increase. So on the x-axis, we see that the saving increases when the cost is cheap. Cost is cheaper. The MRT cost is cheaper. The savings is more. When the MRT cost is more, the savings is less. And this is for the small networks, like less than 40 customers. This is for the medium customer. This is for the large customers. So in every customers, we see same patterns. MRT becomes more expensive, then savings sinks, and eventually in these cases almost vanish. Additional lines then provide little benefits. So these provide some little benefit, otherwise almost vanish. So MRT cost when high, the sensitivity so that the savings is less. So if we want to use more MRT, I think then we have to reduce more cost on the MRT. That from the sensitivity on the systems. And about the vehicle capacity and cost, we may see, the vehicle, each curves correspond to the cap and cost, because we have to vary two things together, cap and cost. As when the capacity is less of the vehicle, the cost is also less. When we search the type A logistics systems, if their capacity is 65 units, the cost is near about around 12, and the 100, the cost is around 15 NTD, like that. So 225 is our assumptions, and these are the variances. So each curve corresponds to a cap and cost combinations for all network sizes. Increase the number of MRT lines, monetarily reduce the average vehicle mileage. Higher capacities or lower vehicle cost slightly reduce the marginal benefit of the additional MRT lines, especially for the large instances, sometimes maybe they are layout problems. So that's why they use this type of some scenarios. And overall, we say that the qualitative benefit of MRT means the less diving is robust to reasonable changes in vehicle capacity and cost. So in conclusion, we may say that we propose here a new variant of capacited vehicle routing problem called capacited vehicle routing problem with public transit and parcel lockers, integrating the public transit and parcel lockers. We developed a mixed integer linear programming model that supports 3 types of delivery modes: home, self-pickup, and flexible, and includes MRT-based parcel transfer as of the routing logic. And the model is tested using both synthetic instances and real-world case based on the type systems, solved using Gurobi solver and the hybrid LNS also. From our experiment, we draw some key insights. The public transport enhances delivery flexibility, but its actual use depends on how network is designed. While MRT integration can reduce total distance or cost, it's often increase the computational complexity. That's why we need some good heuristic algorithm to solve that. Finally, flexible customer types and lockers availability play a critical role in the improving overall routing efficiency. So in these slides about the future research, we extend this work further. We identified some main directions. Incorporate demand uncertainty, something like that. You can extend the model to handle the stochastic demand and delivery failures, that sometimes the delivery failures using robust or stochastic programming, and sometimes integrate real-time MRT, because we have a real-time data, how the MRT will come that stations. So we can use that real-time data, that real-time dynamic MRT schedule, transfer the parcels. And another thing is, I think, crowdsource and dynamic traffic. We can use the crowd. They can they can deliver the parcels from the MRT stations by cycles or bike when they move from one place to another place. So on the way, they can deliver their parcels to the other home delivery customers also. And also email for stochastic time dependent routing. Sometimes if we stochastic time dependent, then this Markov decision process, this type of network can be handled by the machine learning also. And prime customer prioritizations, that is, if we want to give some prioritize these customers, that these customers needs prime customers, ensuring faster delivery using advanced scheduling systems, so on dynamic real-time decisions. The following slide lists the key references and previous works that supported our modeling formulations and case study designs. These includes foundation papers of capacited vehicle routing, public transit, locker-based delivery systems, like this. Okay, thank you so much.
Thank you, Dr. Dash. If anyone have any question, please ask freely. Dear participants, if anyone have any questions, ask.
So, hello, Dr. Soman.
Yeah, sir.
Yeah. So, you have presented a very good theme, and it is the matter of your talk is real life situations. What you have covered here, nice. I have a small query to you. Is not just question to you. What methodology you have applied for solving your model? Did you find any kind of computational complexity of the problem? Did you calculate the computational complexity of your problem whenever you apply the hybrid method?
We actually calculate the computational time. And as we know that routing problem is one of the NP-hard problems, so that's why we don't calculate this type of any formula that this is NP-hard or super NP-hard, something like that. Because this is already well known. And when we add something there, so it should be more complex. So that's why we just calculate the computational time. And compare the exact solver. So from that we can see that the computational time is very less. We can say that by our algorithm, focus algorithm.
Did you compare the solutions with the state of the art
Yeah,
in your direction?
state of the art with Gurobi solver. Yeah.
Or did you compare in
Yeah,
other method?
yeah, we compare with the exact solver, not the other heuristic. We compare with the exact solver, Gurobi.
Okay, thank you very much. Thank you very much, Soman, for your nice talk. Go ahead.
Hello. Hello.
Yes, you
Yes,
can
yes,
say.
yes.
Yes.
Actually, yes, sir, Dr. Somen, sir. I have one question.
Yeah.
My questions is regarding the future scope of your work.
Hmm.
Is it possible to incorporate non-linear programming problem in your problem?
Actually, non-linear, we generally, we have sometimes non-linear, but we have to do that linearize. Otherwise, that complexity, the time complexity, that Gurobi solver, exact solver can't solve that. Because if you see, I think in my model also that, let me see. I just first the objective functions. I think, yeah, this one is one variable and this one is one variable. Two variables multiply. This is the binary variables, not the continuous variables. But that time we see that the computational time is very high by the exact solver, because when we propose some algorithm or something, that we have to see that this algorithm provides good solution. That good solution, how we know that? We have to use some solver or some well-known structures, that from that we can compare that our solution is okay. Sometimes heuristic also gives some solutions that are not okay. So that is the main issue. So if we can easily provide the nonlinear formulations, but we need to linearize that to solve in the solver by the solver. Maybe some linearization relaxation.
Okay. Okay. In the slide number 23, 24, and 25, I observed M0 is 0.
Hmm.
Nothing is there.
Yeah, nothing is there means
Yes, I want
yeah,
to.
yeah. Actually, we want to compare that. Means N0 means there is no public transit, no public transportation system. This means like traditional routing problem. So these from that we calculate the cost. So if we allow the MRPs, how percentage, but how much cost we can reduce that, like that. So that's why we don't provide anything there, because we compare these results to these results. Means 186 is compared to this.
Okay.
This is our first outcome. Yeah, like that.
Okay. Thank you, sir. Thank you.
Okay, thank you, sir. Thank you so much, Dr. Das, for your detailed and thought-provoking talk. Your global research perspective has truly added a depth to today's session. Thank you again. We proceed now the final session. Now, our honorable principal said with us. We request to you, sir, to say something for today. Sir, over to you.
Thank you. First of all, warm welcome all of you. Our college, Sitananda College, Nandigram, Department of Mathematics, organized international conference on contemporary mathematical problems. Today is second day, and last day was first day. And this is very good topic they have selected, and all the organizers, oral young teacher, or the organizer support organizing secretary Dr. Arpun Dhada and Dr. Dipanjana Das, and joint organizing secretary our Saroj Mondal, HOD of the department. They have organized. I am very much pleased, and I am giving them many thanks. And now, as second session is going on, and many scholars, teachers, eminent persons are here all are listening, and many of them will present their very important and valuable lecture, which will be very good and asset and austere for the student and also the researchers and participant, all others participant. Here I want to give an example about the importance of mathematics. Once I was in journey, bus journey. Among the bus, one people asked me, that how this Howrah Bridge is existing, how this Howrah Bridge is hanging over the water without pillar. And one people answered me and asked me, you know, but uh, do not have the idea about the value of mathematics, sir. He asked me that this bridge, Howrah Bridge, is hanging only because of mathematics, only because of true calculation of mathematics. So, without mathematics, each and every subject will not complete, will never be complete, or maybe never be research, or never we can take a step regarding project and regarding any type of research. Suppose uh, many students are there, they are studying history, but in history also mathematics is needed. Suppose they will calculate age of the earth with the help of C14 method, they will calculate. So without the mathematics, all the subjects are incomplete. So today many scholars are here, present here, and the students are also listening. We should follow, we should give the value of mathematics. We should love mathematics. Being a student of other subject, but without mathematics, we cannot proceed in each and every where, because its value is everywhere. Suppose in engineering field, suppose in earthquake, suppose in tsunami, we have to calculate how wavelength of tsunami will reach and when it will come. With the help of, we may predict, with the help of calculation, with the help of mathematics, we may predict. So it is very, very important, and I honor mathematics. I honor most mathematics subject because I am a student of geography and I am a student of environmental science, because in my student life and during my research of the scholars, without mathematics, it is incomplete. So many, many thanks who are participating. Many, many thanks. Please be present and listen. And the paper presenters who are presenting paper, suppose today 26 scholars, teachers, and students will present, and some disciplines are already being already being prepared with the, as per our schedule, we have to follow. Suppose some stipulated time are allotted, within that stipulated time, we have to complete. And I request all the presenters, paper presenters, and also honorable chairperson who are chairing the session, please do continue and please maintain time. Many, many thanks. I hope that this international conference will be in the position of very good. It will get grand success, and I wish from my text it will be success. And I never thought that about 60, more than 60 papers are there. They have submitted. Last day, many papers already being submitted, and today also they will submit 26 papers. So anyway, I do not prolong my lecture, and because I am not expert in mathematical field. Anyway, who are participating, please, as per our norms, continue it. Many, many thanks. And last, I want to extend my thanks to the Department of Mathematics, Sitananda College, Nandigram, because uh, with the help of their contribution, and they are giving labor from morning, night, every time, all time for the success of this program. Then many thanks to all. Please continue the program.
Thank you, sir, for your words which enrich us. Thanks. We proceed now the final invited lecture for this session. Our third invited speaker for the day is Dr. Sholil Ghosh from the School of Mathematics and Statistics, Beijing, China. Dr. Ghosh's work spans significant areas in pure and applied mathematics with emphasis on structural modeling, optimization, and epidemiology, basic mathematical modeling. He has good number of publications. The title of his lecture is Unraveling uh, Leprosy Pathogenesis, a mathematical modeling perspective on disease progression and therapeutic intervention. Thank you, Sholil. We are honored to have you with us. Please go ahead, and the stage is yours. Sholil, over to you.
Okay, thank you, Dipanjana, for introducing me. I would like to thank all of the members of the organizing committee and Sitananda College for inviting me. It's a great honor for me to share my thoughts and research ideas with all of you. And I also like to thank everyone, the audiences presented here. Okay, is my screen visible here? Can anyone
It is
confirm?
visible. It is visible, Sholil. You can we can see this in the small portion.
Okay, no problem. Mm,
Full screen. Please do full screen.
Now
Okay.
is it okay?
It is very good.
Okay. So yes, as Dipanjana already introduced me, I have been doing serving as a faculty and researcher in School of Mathematics and Statistics in BTBU, Beijing, China. So the title she has already presented. My research topic is completely related to disease dynamics, exploration of disease dynamics through mathematical modeling and in some portions statistical inference. So today I will present about a lecture about the disease leprosy. The first thing that why I choose this disease as it is a very much neglected tropical disease, and previously we have done a vast literature review about leprosy. We can see that all of the existing investigations about leprosy, all of them were in population level. So we have dig deeper and try to investigate it from the cellular level interventions, if there is any. So these are the topics of discussion for today. Now, now let me give a brief overview of the disease leprosy. It's an ancient disease. It started in the 18th and 19th century and also existed before the 19th century. Mycobacterium leprae, that's bacteria which is primarily primary reason for the disease. It affects the uh, healthy swan cell. I am showing you the picture nextly there. There are some clinical symptoms of the disease. As you can see that it affects human body through nasal secretion mainly. It's an infectious disease, and it's mainly skin discoloration, or there are some dry skin or painful ulcers in the soles and feet, and in some cases irreversible nerve damage. That's the most compelling angle as a clinical therapeutic approach. Okay, so we first started this journey from decoding a component of nervous system, which is we call, you already everyone knows that it's a neuron, which is the primary component of a nervous system. And within a neuron, there are several portions. We are mainly interested in the portion of these myelin sheaths in the axon portion, and there are some very small cells we call that swan cells. This is mainly responsible for nerve conduction. So what happens whenever M. lepti bacteria infects a human body through any medium or any mode, it affects mainly this swan cell. And there are some other sources which are saying that there can be other modes of interactions, but most of the sources confirms us that this M. lepti bacteria has a special affinity for the swan cells. The swan cells is also a very good topic of research. Scientist Theodore Swan first invented this cell, and after his name, the cell, we call it swan cells. So that's the basic infection dynamics, and depending on that, we have first proposed a basic three-dimensional system. These are the objectives. Okay, so we first proposed this system of a healthy swan cell, and in case bacteria infects that cell, the cell becomes infected one, and there is another population we call the bacterial load or bacterial viability. So there are three population, and these are the interconnections of their interactions. We call purposely, we choose that logistics, proliferation, growth for both the healthy swan cells and the M. repli bacteria. And here the most compelling parameters are the carrying capacity, which we call K1 and K2 for the healthy swan cells and the bacterial portion. We have faced a little complexities during the formulation of this model due to these bacterial clearances. There is a long-term debate going on over that whether bacterial clearance really needed to be incorporated in the mathematical model. So scientist Robert R. Smith, he first suggested that yes, we indeed need to incorporate this one. And after we have done rigorous investigation, a biological and clinical literature investigation, that how much important that if we need to incorporate the bacterial clearance. Otherwise, in most of the cases, you can see that bacterial clearance is not usually incorporated in a mathematical model whenever we are investigating a disease dynamics. And all the parameters, this lambda 1 is the natural infections, and alpha, it is called the bacterial proliferation or generation of new free bacteria from the infected cells. So that's a basic framework. And these are the parameters. I have not listed the source of these parameters here. It is included in the references section. Okay, so first we have analyzed this model analytically, and we have first reproduced the basic reproduction number R0, what we call. And depending on the basic reproduction number, whether the system always remains asymptotically stable or sometimes go otherwise, that become unstable or chaotic, whatever it is. We don't investigate the chaotic nature yet, but for the first phase, we have called that that's a transcritical bifurcation occurring here. So whenever we have that any taking R0 value less than 1, the disease-free equilibrium is 0. It remains stable, and otherwise that means for R0 crossing the value of 1, it significantly becomes unstable or produces an unstable branch. Okay, these are some mathematical formulations, and that's the Jacobian we have formed. And the characteristic equation derived from the Jacobian. That's the endemic equilibrium stability analysis and utilizing the Raut-Hurwitz criteria. So you can see that all the coefficients of that polynomial A0, A1, A2, all of them are analyzed here. And these are 3 restrictions included here. If all these restrictions hold, then we can call that all the eigenvalues of this Jacobian will remain in the left half plane. That means that we can call that endemic equilibrium locally asymptotically stable. That means it does not fluctuate. It can fluctuate in the initial times, but after some times or eventually it will necessarily converge to a stable point. I will show that dynamics numerically later. So now the most important part of this formulation, we are now making it a little complex, and not much complex. We are introducing the essential drug therapeutic interventions. Whenever we are investigating a disease dynamics from the cellular level perspective, then only decoding the disease is not sufficient. Most of the cases we check the drug intervention scenarios, and we try to find an optimal therapeutic domain or regimen for the drug schedules, because we need to always focus on the cure or intervention schedules of a disease. So in this case, we have introduced 2 drugs, U1 and U2. They are obviously time dependent. I have not explicitly mentioned the restriction of U1, U2. Yes, it always lies in between 0 and 1. The lower bound remains 0 and the upper bound remains 1. And we have introduced that in the manner 1 minus U1 in the bacterial interaction, and obviously it will be reflected in the second equation, and it will also be reflected in the third equation during the bacterial clearance. And the second one, we call that the drug dapsone. It explicitly acts against the new replication of the bacteria. So the 2 drugs, they have 2 different dimension. U1, the ofloxacin, it prevents new infection. It prevents the attachment of a healthy swan cell and bacteria. And the second one, U2, it actually kills the bacteria, or someone calls it inhibits the bacterial proliferation. So that's why it's included in the bacterial growth rate. It explicitly shades its impact on the bacterial growth. Okay, and these are the usual initial conditions presented here. So next we investigate the control induced system. You can see that the restrictions are presented here. That's the Jacobian we have formed. That is an objective function. We need to optimize it for making the drug schedule the most effective, as well as it can be also the cost efficiency. We have not done the cost efficiency analysis here, but we can propose the objective function in this way. And that's the theorem. We now apply the great scientist Pontryagin minimum principle or maximum principle. Both are 2 phases of a coin. Someone use it as minimum and someone use it as maximum principle. as we try to reduce the healthy swan, we try to reduce the infected swan cells and try to reduce the bacterial load, as well as or simultaneously we try to increase healthy swan cell population. Now there is an interesting thing that whenever bacterial load decreases into the human body or the infected cell counts declines, automatically the healthy swan cells will increase. The human will get much better day by day. So Pontryagin minimum principle is applied then, and we can extract the control profiles of E1 study and E2 study. Okay, now as we have completed the analytical sections, this is the numerical illustrations. As we have already previously discussed analytically about the transcritical bifurcation. So this is the R0 is going through the x-axis and all the cell population, how they behave when R0 proceed towards the real line from 0 to the positive side of real line. So we can see that whenever R0 remains until 1, the healthy swan cells concentration remains quite okay. But whenever R0 becomes greater than 1, the infection invades explicitly into the healthy cell population. So the infected healthy cell counts decrease, and as well as the infected cell counts increase, and in some other way or some almost similar manner the bacterial count also increase. And nextly, there are the trajectories of the fixed control system. That's for taking U1 equal to 0.7 and also U2 equal to 0.7. Here the inset figures, that is this minimized version, they are denoting the trajectories without control, that is for the first proposed system. And this actual figure which is in the scale of t by 100, it is actually denoting the control system. Okay, so it's not explicitly written here, but I can give you a brief overview. We have introduced 3 strategies here: strategy 1, 2, and 3. And the first cases we have considered whether ofloxacin alone can tackle the disease burden, or whether the second drug, dapsone, can tackle the disease alone, because we need to think about the drug cost efficiency, as well as we need to think about if there can be any adverse drug therapeutic effects. So we have first tried out the monotherapy or the single therapy. But essentially, we can see that whenever both U1 and U2 is a non-zero quantity, and it works like in this optimal domain or optimal region, they can be the most beneficial for our system. As you can see, the term I have used, beneficial, and it means necessarily that the healthy swan cell counts increase, and after some time it decreases a little, but it remains stable up to the concentration of nearly 525 to 530. And the infected cell counts decrease, and also the bacterial counts decrease. Here, this is the profile of U1 star, and this is the profile U2 star. So for the first few days, remember this is a scale of T by 100. So whenever we are taking the index 0.4, it means this is we call 40 days, and 1 means this is we call 100 days. So nearly about 40 days for the U1 study, and nearly 60 days for U2 study, the optimal control therapy remains fixed or acts or behaves like a fixed one. But after that, whenever the initial bacterial load gets cleared and the infected cell counts decrease a little, the two combined drug therapeutic schedules captures or dominates the system very much well. And after that, this can be decreased up to 0. Okay, so for the second phase, we are trying to incorporate a discretized system, and there we have incorporated a new parameter into the system. We call it a shape parameter, and it's going to be okay. That was the primary system we have earlier discussed, and now this is the discretized version where we have incorporated, instead we have incorporated a theta logistic growth of the bacterial population instead of the classical logistic curve. So what are the advantages? We don't yet know about the advantages. We will investigate and we will visualize that later. But for there can be an intracellular competition. Some literature says that there can be an intracellular competition between the bacteria themselves within the human body. So they will enter a healthy cell, they will try to form a safe haven or safe niche or habitat for their for to live or sustain there. And in that scenario, intracellular competition can be builded up there. So this logistic term is rephrased as the logistic term, and we call the parameter p, it's the step size, and theta, we name it the curvature of that relationship. So we next investigate some analytical portions of this, and that's the usual equilibrium analysis or stability analysis. As you can see here, we cannot utilize the Rao-Hurwitz criteria as it is a discretized version. We have introduced the jury condition here, and for that components phi 1, phi 2, they are modulus quantities. According to them, we have introduced 3 new restrictions here, that if these 3 conditions remain hold or restrictions hold, then we can call this, that discretized systems will be stable at the endemic equilibrium E star. Now there are some simulating examples which can be interpreted as the first one. We have defined 3-4 types of curves here, and you can see that for theta equal to 1, theta equal to 1.5, these two portions are discussed here for the proposed system. And there are 2 types of trajectories. One is the solid lines and one is presented the dotted lines for theta equal to 1 and for theta equal to 1.5. 1.5 represents the dotted lines. And now it's an interesting thing that for theta equal to 1, this discretized version actually becomes the classical logistic one. That is the first proposed system. So we will investigate for 2 types of values of theta. If we increase the value of theta much greater than 1, and obviously within a permissible range, and otherwise we investigate the values of thetas much lesser than 1, that is suppose taking 0.5, 0.7, 0.3, 0.1, like that. So the lower portion in figure 2, we have given a numerical example for all trajectories of all the system dynamics, and for theta equal to 0.5. So you can see that for theta equal to 0.5, we can perform a damped oscillation. So what we call the damped oscillation, what is it? It's showing that in the initial phase we can see a little fluctuation, but the modulus amplitude of the fluctuation, all of them are decreasing with time, and after some times, like 1.5 day or something, 1.5 day, that's a t by 10 to the power 4 scale. After some time, it becomes ultimately stable. To a stable concentration it arrives, and not only for the healthy swan cell population, for also the bacterial population and the infected cell population. And in the next figure, if we investigate it again for some much reduced value for theta equal to 0.3, so we can see that the oscillations remains much higher, and it is showing no symptoms at all to converge to a stable trajectory. You can see that it's oscillating for an infinitesimal time. So in this case, the system we call that the endemic equilibrium become unstable in that case. And it happens for all the system populations. Obviously, one have an cumulative effect on the other population, and the other population also have an cumulative and back and forth effect for all the populations. The next one present these all trajectories, that what are the cases of theta when the system behaves like a damped one or a stable one, and in some another cases they behave like a complete unknown character, or a not chaotic one still, but an fluctuating character or too much oscillating pattern the system is showing. So this is completely captured by the bifurcation diagram. And in that bifurcation diagram, we can see that for the value of theta, nearly, I forgot the accurate value, it is nearly 0.48, like that. So if we decrease the value of theta from 1, that is from the classical logistics scenario, for 0.8 up to 0.8, the system trajectories remain stable. But decreasing it more than 0.448, it certainly opens two different branches. And that's the point where the bifurcation occurs. So the system dynamics become unstable in that case of the endemic equilibrium. Okay, so for the next phase, the system has been incorporated with some another tools, and we call it intracellular delay. So there is a good story behind that whenever M. lepri bacteria infects a healthy swan cell, the healthy swan cell does not become infected instantaneously. And there is a simple time lag or time delay behind that. So if we investigate through a classical ordinary differential equation ODE based system, previous researchers in this domain have explored that the system does not accurately showing the behavior in the real world scenario. So that's why we have incorporated a simple delay time lag tau into the system dynamics. And we have provided two different versions of that system. One version is presenting delay in the term lambda 1 SHP in the second equation, and one version is showing the delay, incorporating the delay in both of these branches, that is the minus lambda 1 SHP and also in the plus lambda 1 HSP. So the first one, minus lambda 1 SH T minus tau B T minus tau, this is showing a delayed dynamics. It is signifying the delay in the attachment term. That is, whenever a bacteria gets attached with healthy swan cells, the healthy cells does not become instantaneously an infected one. And the second one, the counterpart which is getting added or going to the infected portion, this is plus lambda 1 SHT minus tau BT minus tau. It is showing that whenever a bacteria infects a healthy cell, yes, okay, the cell becomes an infected one, but the cell, whenever it becomes an infected one, it does not also instantaneously try to produce new free bacteria. So there is also an intracellular delay working behind that. So these are the two versions of delayed model we take the job to investigate. And let's see, yes, these are the usual equilibrium analysis, but in these cases the analyses are much different. As for a delayed investigating a delayed differential equation system, you can see that we cannot actually go to the classical ones approach, because the Jacobian matrix of a delayed system, whenever we try to build a characteristic equation, it becomes actually a transcendental equation. You know the transcendental equation, that's a very basic one from the calculus and geometry. A transcendental equation produce infinitely many roots, and they are whatever they are, they can be purely imaginary, or they can be purely real, or they can be a mixed ones. So for the delayed system, the theory gets much complicated one. And we are now trying to investigate the case where the roots, what are the conditions when the roots will become purely imaginary. So what happens when the root becomes purely imaginary? We will see that next. These are the processes of the we are when we are trying to find out the conditions. And as you can see that we have, in generalized version, we have taken rho equal to I omega tau. So we are taking a purely imaginary portion and trying to investigate what are the conditions. So yes, we have arrived at a theorem here that this gamma 1, gamma 2, and gamma 3, they have some restrictions. And in these cases, the delayed system will be locally asymptotically stable for all tau greater than 0. Now we are coming to the existence and obviously the emergence of Hopf bifurcation, the most novel phenomena of these sections. And according to Butler's lemma, we have provided a critical value of tau, and we call it tau 2 star. And we can see that for any value of delay, tau is less than tau 2 star, and for the cases of tau greater than tau 2 star, there are two different dynamics the system are showing. One is asymptotically stable version, and the other one is unstable version. And this mathematical formulation of this tau 2 star is represented by this equation. So what is the biological significance behind that? We will show that numerically, but let me give you a brief overview that whenever tau gets very much close to tau 2 star, the bifurcation occurs. That we can see the fluctuating dynamics, that the system is suddenly showing up fluctuating dynamics. And this tau 2 star, we have considered this for the second system. And I have not mentioned another one which we call tau 1 star. That is also in a similar way we can get the value of tau 2 star for the first system, tau 1 star for the first system. That's the critical value of delay for the system 1. Okay, and nextly we have incorporated again that optimal control induced mathematical model. And for over the delayed system, we have again applied the optimal control. And for the two drugs here, we have applied the optimal control U1 and U2. So we are trying to compare all the systems here. Now we have so many systems in our hand. One is the basic three-dimensional system which have no control. The another one is a control induced system, but no delay is attached here. The second one is the delayed version, but the delayed first version 1. And the fourth one is the delayed version, which is delayed version 2, but still no control introduced over the delayed system. And then the final two, that the delayed version as well as the optimal control schedules are incorporated there. So maybe six systems we have already built here. So yes, these are the Hamiltonian. This is the Hamiltonian H and the optimal control profiles. It becomes a little hazy. I don't know. The optimal control profiles E1 star and E2 star for the system 1, and control profiles of E1 star and E2 star for the system 2. Okay, now we come to the comparison part. So this first figure is showing the trajectory for the non-delayed system, that is system 1, and the second one we are comparing the fast delayed system, and here we are taking tau equal to 2. You can see the color discrimination here. The red color indicates the system 1, that is system without delay, and the blue one, as you can see, that whenever you incorporate delay and taking the delay tau a little large, I am saying the term a little large, it has no mathematical groundation, but I will show you in the next slide what is the reason behind first choosing tau equal to 2. There is a specific reason behind that, choosing tau equal to 2. We wanted to show the oscillatory dynamics at the first picture. That's why we have taken tau equal to 2, nothing else. Okay, and for the second one, we have compared all these three systems: the system without any delay, the system, the system with delay for tau equal to a little value, that is nearly 0 value, 0.01, and tau equal to 2 and tau equal to 5. So for tau equal to 0.01, obviously it is expected that the system will not show much oscillating dynamics. Obviously, the trajectory colored in red. And if we increase the value of delay, tau equal to 2 or tau equal to 5, we can see that the amplitude of the oscillations as well as the magnitude obviously also are increasing much higher than the previous scenario. So what do we get from this? Okay, there is another one. We have now chosen a specific value of tau, that is tau equal to 2 again, and compared the three systems in a row. The first one is the system without delay. The second one is the fast delayed version, and the third one is the delayed version 2. So three system has been manifested. Everyone you can visualize that here. Okay, for the next diagram, this is the biological portion. We can have a novel biological insight from this, and the insight is that I was talking earlier, that why did we choose the value of tau equal to 2 there to show the oscillating dynamics in the first hand. Yes, because whenever we build the system, we first numerically assess its dynamical nature. And first try to investigate, the first job was actually whether it is showing a periodic solution. So for a system with a simplistic delay also, maybe it's one in one term or in two terms or in a nonlinear term, or maybe it can be a linear term. The system will need to show always oscillatory dynamics. But what are the restrictions of tau? So we have first produced this bifurcation diagram for our system, but for the presentation I have rearranged all the diagrams here. So the value of tau equal to 1.39, that's the critical value. So if tau 2 star, we have not showing the picture of tau 1 star here. tau 2 star, whenever it remains less than 1.39, the system remains stable, and for whenever crossing it is crossing the critical value 1.39, it shows periodic solution. And you can see the three-dimensional limit cycle solution for the system also, it is presented here. Okay, the next one incorporates the simulation for the optimal control induced delayed system. And for both of the systems 1 and the 2, the version 1 and version 2, you can see that the red and green trajectories, and the red one is depicting the dynamics for system 1 and the blue ones depicting the behavior for system 2. And in the second phase, the optimal solution, all solutions are also investigated for also the delete system 1 and delete system 2. So you can see that the blue trajectory here incorporates U1 star for both of these simulations, and U2 star is being indicated by the red trajectories. So you can see that the delayed system 2 is much realistic and showing much promising results in this case. You can see that in the first hand, that if for the delayed system 2, the healthy swan cell populations is decreasing much rather than these green trajectories. And for the same similar pattern happens for also the infected cells and the mLEP bacterial load. But for the optimal control profiles, I can give you a very simplistic view that whether this pattern is getting showed here. For delay system 1 and for delay systems 2, you can see that both of these trajectories behave in a similar way, but they have differences in nature, obviously, as far as the numerical ranges are concerned. So for the initial times, nearly it is maybe 130 days, as far as I can remember, 130 days, the control profiles can be a little low, and then it should be, or it necessarily be increased up to the day 1700, and it can be varied within that a little, and after that it can be decreased. But it is I am showing you this for the optimal profile of U2 star, and for U1 star the dynamical nature is different for system 1 and system 2. Okay, so we come to the next portion here. A different mathematical framework has been presented, and as you can see, the sub heading of this portion, we call it, we are trying to critically observe the WHO recommended multi-drug therapy on the disease leprosy. So what is WHO? We will already know, that's the World Health Organization. Now there are many researchers in the earlier times who have presented different domains and structures of multi-drug therapy. And maybe 1967, in 1967, World Health Organization first proposed a standard therapeutic domain of multi-drug therapy, what we call MDT. And we feel the essence that we need to investigate, and if we can challenge the WHO recommended therapy. We are not sure at the first hand, but yes, we have some interesting outcomes after framing these systems. WHO recommended therapy have many drawbacks, as who recommended therapy previously in many clinical literatures, mainly in South America and in some portions of Africa, and also obviously in some portions in India. It's showing much promising, but in some countries there are examples of very much clinically different situations or very complicated situations. Who recommended therapy never address the reinfection scenario. That's the most interesting one. Leprosy is a disease which can reoccur with respect to times. So a human can get infected, and with time the human gets hospitalized, and after that that he thinks that the disease he overcome with the disease. Okay, so uh, he come back to home, no problem with that. But after some time, there are some latent bacterial molecules or bacterial or infected cells remains in the body. So with respect to time, like maybe there are some phases and examples of 10 years. A person gets infected and he becomes very much healthy within 1 or 2 months of taking therapeutic intervention. But after 10 years, again, he is diagnosed with leprosy. So that's a very interesting phenomena we need to discuss here. So we have introduced that parameter lambda here, that's incorporating the reinfection scenario. And the parameter alpha, it is considering the natural infection scenario. And yes, we have taken these interactions in functional forms, fx and gx. So fx and gx both are continuously differentiable function, and they obviously they have an infimum and supremum as well, and we have taken this as 0 and 1 back and forth. And obviously fx can need to be a monotonic increasing function, a strictly monotonic increasing function. And obviously the counterpart gx, it needs to be continuously monotonically decreasing function, a strictly monotonically decreasing function. Okay, and the MDT drug therapeutic schedule DXDT, this equation is formed as, because all the other equations it is very much simplistic, so I'm not going into detail. The DXDT portion is a little interesting. It is incorporated as E eta SI minus theta x. Obviously, this theta, it is the drug clearance rate that within the daily metabolic activities, whether you are running or you are going in a gym or you are doing any hard work or hard tasks. So the drug interventions will get out from your body with different mechanistic approaches. And this E eta SI, this eta is the drug efficiency rate or drug efficacy rate. And this SI, there is a Ridley-Joplin classification of leprosy to actually measure the infected cell count. And actually it is not they have not counted the infected cells. Actually they have counted the viable bacterial load presented within the infected cell. And according to that, in a proportionate manner, we have considered the term E eta SI. And this E eta SI is actually presenting in which way we are trying to administer multi-drug therapy into the system, that is into the human body. So we have considered this small e as the proportionate constant, and this eta, it is the drug efficiency rate. Okay, so next we are trying to find some analytical overview. You can see there. Okay, coming to the numerical simulation part. So you can see that for eta equal to eta star, that is 0.024, you can see that the Hopf bifurcation diagrams in the first phase. And for the picture in the second phase, you can see that we have performed most needed sensitivity analysis of the combined parameter impact. That is, one, we have taken beta, that is the natural infection rate, and one, we have taken eta, that is the drug efficacy rate. And the treatment we have scheduled is as for an example for 100 days. So you can see that this is beta is going on the y-axis, and it is we are doing it with respect to time. And the color graph, it is whether it is getting warmer or it is getting much cooler, what are the scenarios is happening here. The next one, we have presented two contour plots with respect to the basic reproduction number R0. And in the along the x and y axis, there are two parameters. One is eta and one is lambda. And for the second one, eta and beta. So just changing the pair and see the differences if there can be observed any. The next one depicts the point care section for the set of parameters for system 1. So we have shown 6 point care section, and we have shown that for the infected cell counts, with respect to the infected cell counts, and we have taken different values of eta here, that is 0.02, 0.021, 0.023, and we are going up to 0.026. So you can see that a strong pattern is getting observed here, which further imply a necessary biological meaning or biological context. Okay, for the next one, okay. For the next one, I am getting reminder that I am running out of time. Okay, no problem. Okay, I can go to the conclusion part. For the next one, we have incorporated the memory effect into the system, and we have performed Caputo-Fabrizio analysis. Caputo-Fabrizio fractional operator has been incorporated into the system. These are some simulations from the memory-induced system, and there are some others which is called CFOC, the Caputo-Fabrizio introduced optimal control system. And that's the control schedules for the integer order model. Whenever we are taking the order of the fraction derivative zeta equal to 1, or we are taking different values of zeta, and for u1 star and u2 star and everyone else's. So a fractional order for zeta equal to 0.6, this is showing a much promising results. That is the control schedule for u2 star, and the green one is showing u1 star. Okay, and this one is the last one, and here we have incorporated a stochastic version of the mathematical model we have earlier framed for challenging the who recommended dynamics. So here we have introduced a new transformation pathways, and you can see that after investigating the quasi-stationary approximation, we have find out quasi-steady state approximation, we have find out the deterministic version of the modified model. Okay, this one is representing the transition state table. There are 7 transition happening into the system, and this is the much needed Kolmogorov forward equation. Our aim is to find out through all these phenomena, checking the phenomena, so whether it is quasi distribution or exact distribution. We are finally trying to reach to the uh, e- expected time to extinction for the disease. So yes, there is much needed application of this Ornstein-Uhlenbeck process also. And yes, this E tau is giving us the quantitative measure of the expected time to extinction. And these are some numerical simulations depicting the system dynamics or trajectories. And yes, you can see that the first one is the quasi-stationary distribution of the infected cells for taking 3 different values. And yes, it follows the normal distribution. And the second and third one, we have investigated the expected time to extinction, and we can show that if we increase the drug efficacy rate from 0.22 to 0.28, and there can be a little much one. So the expected time to extinction of the infected swan cells into the human body can be decreased very much realistically. And these are some very much interesting 3-dimensional contour plots connecting from that Ornstein-Uhlenbeck process. Okay, these are some novel conclusions of the study. I think that the novel conclusion I have already discussed there during describing each of the portions of the study. Okay, and the whole presentation is based on these following published literatures of my, and there are some ongoing works as well. And these are the references. Thank you. Now you can ask me some questions if you want.
Participants, if you have any questions, please ask Sholil. I think Sholil, there is no questions from the audience.
Okay.
But thank you so much because your presentation is very nice and very enlightening ideas, which is very knowledge provoking also. Thank you, Sholil, for your illuminating presentation. Thanks for giving us such a nice presentation and your precious time.
Okay, thank you very much. I also sincerely thank everyone presented here, and especially the authority of this conference committee, and especially to Dibanjana and the principal sir for inviting me for this lecture. Thank you, everyone.
Thank you, Sholil. Thank you. With this, we conclude the invited lecture segment of day 2 of ICCMP 2025. I extend my heartfelt gratitude to all 3 distinguished speakers for sharing their knowledge with us, and to our global audience for joining us and engaging with today's discussion. After this session, we will meet you soon at 2:10 p.m. There, we will resume with the paper presentation session, Group C and Group D. Thank you. Please stay connected and rejoin us after the lunch break. Thank you.
হ্যাঁ দীপা,
হ্যালো,
হ্যাঁ হ্যাঁ
খুব ব্যাপক হয়েছে, ব্যাপক কাজ করিস তো রে।
Okay, so am I audible?
So welcome back to this session. So this session is for the paper presentation of Group C participants. So in this session, the chair will be handed over.
Very good afternoon, sir.
This session, very good afternoon. This session will be chaired by Dr. Shoikat Saha from IIT Roorkee. And already he has presented his talk in morning session. So please continue, Shoikat Saha. Please, sir.
Yeah, so the first talk is by Raja Shekaran K. So is Raja Shekaran K available? Raja Shekaran, are you available? Yeah, so Sharoj, should I call the next participant?
Oh, next one.
Yeah, Kaushika K.
Yes, sir, I am available, sir.
Yeah, so where is Raja Shekaran? Because you belong to the same institute.
Yes, sir. He can present second
Ah,
answer.
okay, so
Some net issues.
yeah, so I'm inviting you. So Kaushika, so try to finish your presentation within 6 minutes. Okay, so 6 minutes, 5 to 6 minutes presentation, then 2 minutes question answer. Okay.
Okay, sir. Thank you,
So
sir.
I request you to start. Okay,
Okay, sir. Shall I present, sir?
please.
Sir, is it visible, sir?
Yeah, it's visible.
Okay, sir. So, good afternoon, everyone. I'm very glad to present my work in International Conference on Contemporary Mathematical Problems, organized by Department of Mathematics, Sitananda College, West Bengal. So my presentation is about numerical simulation of hydromagnetic convective flow of hybrid nanofluid flow over a rotating disk. So myself, K. Kausika, I'm a research scholar under the guidance of Dr. P. Suryakumar sir, Department of Mathematics from KPR Institute of Engineering and Technology at Coimbatore. So my present study examines how an applied magnetic field and international heat generation affect the fluid flow and thermal behavior of a water-based hybrid nanofluid, which contains two types of nanoparticles, aluminum oxide and copper, which flow over a rotating disk using one-common similarity transformation and using a MATLAB's BBP force solver. So the dimensional parameters including a magnetic interaction parameter, then Prandtl number, Eckert number, and heat source are analyzed. So these results shows that the magnetic field significantly, which alters the flow structure and which enhances the heat transfer, highlighting the hybrid nanofluid's potential for cooling and many engineering field applications. So introduction. So heat transfer. So heat transfer means movement of heat from higher temperature to lower temperature. It happens in three ways: conduction, convection, and radiation. The efficient heat transfer is essential for maintaining temperature control, which improving system performance, ensuring safe and reliable operation across a wide range of industrial and technological applications. So next we are moving to nanofluid. So nanofluids means mixing of nanoparticles into the base fluids, which enhance their thermal performance. So in 1921, Von Karman first formulated the rotating disk boundary layer theory using similarity transformations. Then in 1934, Cauchy refined Von Karman's rotating disk theory by solving the similarities equations to yield more accurate velocity and pressure fields. So many authors followed this concept and published many papers. In 1955, Gregory et al. And 1978, Bhatnagar and Zago. In 1983, Zizeri et al. Identified mid-radius bachelor profile. Then in 1993, Othkin et al. Identified spiral vortex onset in Old B flow between rotating disks. Then the first concept of nanofluid was introduced by Choi and Eastman. So following this concept, Wong et al., then Maiga et al., then Bajak et al., then Rushdie et al., Turkey in 2014, he used spectral collocation to study water-based nanofluids with various metallic and oxide nanofluids and found copper nanoparticles, which produce the greatest thermal enhancement. Then following this concept, Khan et al., then Ramzan et al., Yasmin et al., publishing the papers. Due to these superior thermal characteristics, nanofluids are widely explored for using electronics, cooling systems, then energy systems, and industrial heat transfer processes. To further enhance heat transfer capability, the concept has been extended from nanofluids to hybrid nanofluids, where mixed nanoparticles offer superior thermal characteristics. Next, we are moving to hybrid nanofluid. So, hybrid nanofluid means mixing of two or more nanoparticles in a base fluid, which enhances the heat transfer. In 2006, Turkey et al. Developed polypyrene multivalent carbon nanotubes, hybrid composites which improved electrical and mechanical performance, which highlighting their potential for energy and thermal applications. Then later, Suresh et al. Suresh et al. In 2012. Then Falla et al., Khan et al., Super et al., then Alkin et al. In 2002. Following these studies, they found that MHD graphene silver and nanofluid over a rotating disk, which enhances the heat transfer. Then in 2013, Yazin et al. And 2024, Chakravarti et al. Then recently 2025, Mishra et al. Studied magnetic radiation and slip effects on hybrid nanofluid flow and heat transfer over a rotating porous disk. So these advancements highlight the strong potential of hybrid nanofluids for high performance thermal management applications. So these are some applications of hybrid nanofluid flow over rotating disk, which is useful in advanced cooling and thermal management, including turbo machinery, high performance electronics, then biomedical and biomechanical systems, including biological sample processing, then energy and power systems, including nuclear reactor cooling, wind energy systems, then automotive and aerospace applications, including brake and clutch cooling, then aerospace thermal control systems, then material processing and manufacturing, including hard disk and magnetic storage manufacturing, then metal cutting and machining, then scientific laboratory research, including fundamental studies in fluid dynamics. So hybrid nanofluid, which are useful in many fields. So the present study examines hybrid nanofluid flow over a rotating disk under the influence of a magnetic field and internal heat generation. So these analysis focuses on the velocity components in the radial, tangential, and axial directions. The dimensional parameters, which includes Eckert number, magnetic field, heat source, and Prandtl number, which are additionally expressed through the parameter. So the alumina and copper nanoparticles is transformed into the
Yeah,
OD.
Kaushika, please
Yes, sir.
wrap it up in 1 minute.
Yes, sir. So, advancing research in this area which helps to develop high performance cooling technologies for future industrial and technical applications. So, this is my schematic representation of the system model. So, this is the cylindrical coordinate r comma theta comma z. This is one type of rotating disk. So, I am placed in a horizontal position. Here B naught is the magnetic field, then omega is the angular velocity. So, this is the schematic representation. So the mathematical formulation, I'm using my reference of Bechek et al. And Tackling 2014. So this is the mathematical representation. Equation 1 is the continuity, then equation 2, 3, 4 is the momentum equation. Then equation 5 represents energy equation. So these are the boundary conditions. Then this is the similarity transformations. So using similarity transformations, the partial differential equations which reduced into the ODE equations. So equation 8, 9, 10, 11 are the ODE equations. So numerical approach, I'm using MATLAB's BB4 solver. So this is my numerical approach. These are the thermophysical properties I taken This is the dimensional parameters, and these are the hybrid nanofluid values. This is the comparison results. This is the computed value of screen friction and nozzle number. So these are the resultant directions. This is the graphical representation of my work. So figure 1, figure 2, which shows the effects of magnetic field and velocity components. Then figure 3 and figure 4, which represents the effects of magnetic field and velocity components and temperature. So this is the effects of copper nanoparticles on velocity components. Figure 7 and 8 shows the effects of copper and aluminum nanoparticles on velocity components. Then 9 and 10 represents aluminum nanoparticles on velocity components. Then 11, 12 shows Eckert number and heat generation and temperature distribution. So finally, conclusion, the study analyzes the flow and heat transfer of a copper and aluminum water nanofluid over a rotating disk. So which enhances the hybrid nanofluids, which enhances the heat transfer. It will be used in many fields. So the results of this study have valuable engineering and industrial application. So rotating disk systems employing hybrid nanofluid can be effectively, which is utilized in heat dissipation and energy generation and cooling technologies. So these are my references. Thank you, sir. Thank you, sir. I finished.
Okay, thank you, Kaushika. So any questions?
Is any questions from audience side?
Is there any question from the audience?
No, sir. No, sir. It's very, very nice presentation, sir. Thank you,
Thank you.
Kaushika.
Thank you, ma'am. Thank you, ma'am.
Okay, Kaushika, so I just have a small question.
Yes, sir.
Yeah, so can you explain in layman's language what is Eckert number?
Sir, Eckert number, which analyzes the heat effect between kinetic energy.
Yeah, so
Yes.
it's a ratio between two things, right?
Yes, sir. It's a
What
ratio
are the
between two things. Sir, kinetic energy and heat generation effects, sir.
Okay, so I know for your study, what is Eckert number? What is the range?
Sir, range means Eckert number is a dimensionless number, sir.
Yeah.
So here I can take some dimensional numbers are there, sir. So in my work, I can take the Eckert numbers, sir.
Okay. Okay, thank you.
Okay, sir. Thank you, sir.
Yeah, next is Raja Shekaran. Are you here?
Yes. Shall I leave, sir? Thank you, sir.
Yeah, you please leave.
Thank you, sir.
Raja Shekaran? I don't think he's here. Yeah, next is Oyon Kanti Pradhan.
Sir, I am audible, sir.
Yeah, you are audible. So yes, please wrap it up by 5 to 6 minutes, then 2 minutes question answer.
Oh, Soikat, Raja Shekaran is presenting actually. I can see.
Oh, okay. Oyon, you please mute yourself. Yeah, Raja Shekaran.
Oyon Kanti Pradhan, you will start after Raja Shekaran.
Okay. Sir, I am present.
Yeah, Raja Shekaran.
Yes, sir.
Continue.
Raja Shekaran.
Yes, sir. Yes, sir.
Yeah, so you are with us?
Yes, sir. Yes.
Yeah, so like, can you switch on your camera and introduce yourself for just few seconds?
Okay.
Yeah.
Sir, I am Rajasekaran.
Yeah.
Sir, I will present the PPT.
Yeah, you may present.
Yes, sir.
So before you start, please wrap it up within 6
sir.
minutes, okay?
Yes, sir.
Please make it in full screen. Raja Shekaran, please make it.
Yes, sir. Yes, sir.
Yes. Right.
Sir, I am visible, sir.
Okay, continue, Raja Shekaran.
Okay, sir. Sir, good afternoon to everyone. I am K. Rajasekaran, under the guidance of Dr. P. Suri Kumar, sir, in KPR Institute of Engineering and KPR Institute of Technology from Coimbatore. My research topic is tangent three-dimensional hydromagnetic convective flow of a hybrid nanofluid flow in the presence of magnetic and electric fields. This is my abstract. This study investigates the unstudied three-dimensional electromagnetic flow of a water-based hybrid nanofluid involving copper and aluminum nanoparticles under the influence of heat generation and thermal effects. The similarity transformations are used for converting the conservation of mass, momentum, and energy equations in nonlinear ODEs. The MATLAB B before the solver is used to solve the equations numerically. This outcome shows the skin friction coefficient reduced Nusselt number, which is determined different values of the parameters. This is my introduction, sir. First of all, I have to explain the heat transfer. The heat transfer is nothing but a movement of heat from one place to another place. The types of heat transfer is conduction, convection, and radiation. Next, we go to the nanofluid. The nanofluid is nothing but the nanofluid is nothing but dispersed in the one phase fluid and one nanoparticles. These are my literature surveys. In the year 1995, Choi and Eastman introduced the nanofluid. In 2009, Leo et al. Are introduced the heat transfer over a bidirectional structuring sheet with variable thermal conditions. In 2017, Nayak et al. Introduced the three-dimensional free convective magnetohydrodynamic flow of nanofluid over permeable linear structuring sheet with thermal radiation. Next, we go to the hybrid nanofluid. Hybrid nanofluid is nothing but two or more nanoparticles are dispersed in the same base fluid. It is called as a hybrid nanofluid. In 2011, Suresh et al. Investigated the synthesis of hybrid nanofluid using two-step method by its thermal physical properties. In 2020, Teleli et al. Investigated the three-dimensional magnetohydrodynamic nonlinear radiative flow of hybrid nanofluid beyond an irregular dimensional surface with slip effects. In 2021, Krishna et al. Investigated the magnetohydrodynamic flow of Cashan nanofluid, hybrid nanofluid over an infinite exponentially accelerated vertical porous surface. In 2021, Zainal et al. Investigated the heat generation or absorption effects on magnetohydrodynamic flow of hybrid nanofluid over bidirectional exponential stretching or sinking sheets. Next, we go to the electromagnetohydrodynamics. The electromagnetohydrodynamic is nothing but it's a conducted the electric field and magnetic field is electrically. In 2021, Zainal et al. Investigated the unsteady EMHD stagnation point flow over a stretching or shrinking sheet in a hybrid nanofluid. In 2022, Ahmad et al. Investigated the convective heat transport in bidirectional water-driven hybrid nanofluid using blade-shaped cadmium and graphite nanoparticles under the EMHD process. In 2024, Ramesh et al. Investigated the electromagnetohydrodynamic radiative titanium oxide and ion ethylene glycol hybrid nanofluid flow over an exponential stretching sheet. These are my applications of hybrid nanofluid. The high performance cooling systems, automobiles and engine cooling, solar energy systems, and biomedical fields, aerospace systems, nuclear and power planets. This is my motivation. The electromagnetohydrodynamic flow has become an important research area because many modern devices use both electric and magnetic fields to control flow
You
in
just have 1 minute.
Sir?
Please wrap it up in 1 minute.
Okay, sir. Okay, sir. Okay, sir. This work is more motivated by the need to create stable, efficient, and high-performance thermal system for modern technology. This is my mathematical formulation. I have used the flat plate in my schematic diagram. This is three-dimensional, three directions: the x-axis, y-axis, and z-axis. I have to using the nanoparticles, copper and aluminum. Next, we go to the partial differential equations, similar transformation, and ODE equations. This is my partial differential equation. The first equation is referred to the continuity, and the second and third are momentum equations, and the final equation is called as temperature equations. This is my boundary conditions. Then this is my similarity transformations. Next, finally, this is my ordinary differential equations. I have to using the thermophysical properties with the dimensions parameters. This is I have to using the thermophysical properties values with hybrid nanofluids. I had to using the numerical method, the boundary value problem 4C. This is my result and discussions. These two figures are referred to the effects of magnetic field on the velocity components. The m increasing, then also increasing the velocity components. The effects of unsteady parameters on velocity components. Next, these two figures are referred to the effects of electric field in x direction on velocity component temperature distributions. The electric field x direction is increasing, so also increasing the velocity first velocity component. Then the electric field x direction in increasing, then decreasing the temperature distribution. These figures are referred to the effects of electric field in y direction and velocity component and temperature distribution. These two figures explain the effects of thermal radiation and the heat source on temperature distributions. These figures express the effects of stretching rate on velocity component and temperature distributions. This is my conclusion, and enhances the magnetic field and electric field, which enhances the velocity component and decrease the temperature distribution. Simultaneously, it's also lead to decreasing the skin friction coefficient and increasing the reduced Nusselt number. The velocity component enhances with increasing the magnetic field and electric field in x direction. Moreover, enhancing the magnetic field and electric field in y direction, further decreasing the skin friction coefficient and increasing the reduced Nusselt number. In the higher values of thermal radiation and heat source enhances, when also enhances the temperature distribution and decreasing the reduced Nusselt number. The velocity component reduces with higher estimation of the unsteady parameter and stretching parameter. However, the skin friction coefficient decreasing and increasing the reduced Nusselt number. These are my using reference. Thank you, sir.
Questions, please. Questions from the audience? I don't think there is any question. So I just have a small question, Rajashekaran.
Yes, sir.
Can you go to the slides where you have written these Navier-Stokes equations?
Yes, sir. Yes, sir.
Yeah, so I see that in your title you have mentioned 3D analysis, right?
Yes, sir. Yes, sir.
But where is the governing equation corresponding to W?
So W equal to 0, sir. W is a zero velocity component, sir.
Then why it is three-dimensional?
So this is the three-dimensional equation, sir. But the W values are also 0, sir.
So if W is 0,
yes, sir.
You see the first equation. So why del W del Z term you have retained?
Sir, 1 second, sir.
I'm saying if W is 0.
Yes, sir.
Why del W del Z you have retained? You have retained del W del Z, right?
Yes, sir.
Yeah, so if you are 0, why you have retained?
So because of the continuity equation, sir.
Yeah, but del W, you are saying W is 0.
Yes, sir.
Okay, you please think about it, okay?
Okay, sir.
Sir, I have a question, sir.
Yeah.
May I? Sir, can you go to the graphical interpretation slides where you have shown the influence of magnetic field?
Yes, sir. Yes, ma'am.
Sir, I have a simple question. Magnetic field generally acts as a damping force, so it is supposed to reduce the flow. But here, in your graphical results, it is showing an increasing trend.
Yes, sir. Yes, ma'am.
Can you just discuss about it? How it is coming like this?
So the magnetic field also increasing because we have to increasing the thermal effect, ma'am.
If there is some other parameter you have combined with it so that the nature is increasing, is there any other parameter with it influencing this behavior or something?
Ma'am, here the magnetic defect, ma'am. Magnetic effect.
Okay, thank you.
Okay.
Okay, thank you, Rajshekhar. You may
Thank you,
leave.
sir. Thank you, sir. Thank you so much, sir.
Next is Oyon Kanti Pradhan.
Yes, sir.
Yeah, Oyon Kanti, you may start down. Please finish it within 5 to 6 minutes. Okay. So yeah, you may present now.
Sir, is it visible?
Yeah, it is visible.
Okay, sir. Good afternoon, everyone. Myself, Ankanti Pradhan, and today I will be presenting on expand dielectric characterization of Teflon at various off-center positions using alternative cavity perturbation. And this collaborative work was planned and executed with Dr. Kaushik Bhattacharya from Tamilnadu Mahavidyalaya. Basically, rapid advancement in 5G or 6G communication networks, aerospace, and other industrial processes presently encompasses with intrinsic sustainable material methods, and thus necessitates unveiling the electromagnetic properties of energy efficient, optimized performance, low loss fabricating insulators or ceramic composites such as Teflon towards terahertz and down to lower microwave bands. Additionally, among the listed sustainable frequency band optimization techniques for efficient dielectric characterization, the non-destructive cavity perturbation method is mostly considered due to structural simplicity, short processing time, high accuracy, and reproducibility, especially for the characterization of low-loss tiny samples in the X-band regime. However, despite several advantages, those includes reliability in measurements and high temperature sustainability, conventional resonant cavity method lack for the uncertainty in characterization arising due to the narrow measurement bandwidth, large MEP size, uncertainty in Q measurement, and constraints imposed because of sample position. So, in an effort to search for the best possible mechanism to address such problems, the conventional resonator structures are upgraded with three necessary instrumental changes. First of all, we have used stadium-shaped iris pattern instead of usual rectangular form for cylindrical resonator and fabricating a diffuse 6 mm circular iris for rectangular cavity resonator. So, secondly, the absence of sample holder inside the physical cavity structure predominantly predominantly eliminates any additional cavity power losses. While by using single detector for simultaneous transmitted and reflected power measurements, inaccuracies in derived reflection coefficient responsible for instrument tolerance altogether eliminated. Uh, the problem with large sample size was minimized by vertically loading the cylindrical Teflon substrate at positions other than the energy maxima points. Further, analytical correction in conventional perturbation theory was subsequently introduced to compensate for these positional changes. So, this is our E111 mode experimental measurement setup for dielectric characterization of Teflon at 8.25 GHz, and this is basically the proto. Oh, sorry, sir. This is basically the prototype of 8.5 GHz TE101 mode experimental characterization setup using rectangular resonator. Here, the terms cos alpha and the M for rectangular resonator, these are the actually the proposed correction factors to the conventional permittivity formula approximated following Gaussian field distribution around the cavity center and calculated from the interpolation functions of the sample's absorption profile. This is actually the sweep frequency reflection coefficient curve for air-filled cylindrical resonator cavity, Here, 8.21 GHz is the resonant frequency traced by adjusting primary attenuator, and the Q factor is determined from the respective half power points measured on varying the secondary attenuator by the dexamer. Similar mechanism was adopted for the rectangular cavity also. This is S21 reflection coefficient curve for Teflon loaded cavity resonator with distinct sample positions. So the table clearly illustrates that. The table clearly illustrates that the experimentally measured dielectric constant values are well agreed with the AI-based extraction, demonstrating an accuracy of around 96%. Dielectric constant measured using cylindrical resonator for samples of any height yields extreme accuracy from 96 to 98.5%. Similar result is depicted for 10.16 mm sample characterized using rectangular cavity structure with error 1 to 1.6%. Overall standard deviation nearing 0.0624 is observed for the cylindrical resonator, revealing outcomes which is higher than the estimated uh, 0.053 derived utilizing rectangular structure, and and in comparison to NIST data, experimental directive losses show significantly better accuracy, nearly 80 to 95% derived by using any resonator types. However, for the comparative study, it is clear that the loss tangent values derived through experimental measurement ranges in between 0.0009 to 0.0013 are highly accurate, with the error limits in between 4 to 30% with respect to the earlier reports. So, in conclusion, experimental measure dielectric constants for smaller and fairly large size, or as for the majorly displaced samples, are much accurate than that obtained for medium-sized samples. High parametric precision at lower X-band consequently ensures its usability at the lower microwave frequencies. Furthermore, this modified numerical approach guarantees significant accuracy even for thicker, low-loss solid materials, irrespective of the sample positions. So in future, we will extend our work to investigate the dielectric properties of larger, high-loss samples employing this novel approach. Moreover, with the aid of this resonator, further research can be carried out to assess the dielectric properties of materials in liquid and gaseous states. And these are the list of references we will share. And thank you.
Questions? There is no question. Let's thank the speaker. Thank you, Ayon. You may leave now.
Thank you, sir.
Okay, our next speaker is Deepika Rani. So, may I request Deepika Rani to respond?
Yes, sir. Good afternoon, sir. Sir, very good afternoon.
Yeah, thank you for joining, and you please share your slides and try to wrap up in 5 to 6 minutes.
Okay, sir. Sir, is it visible?
Yes.
Sir, shall I start?
Yeah, please start.
Okay, sir. Thank you. Good afternoon, everyone. I am Deepika Rani, research scholar from Department of Mathematics, Guru Jambheswar University of Science and Technology, Hisar, Haryana. I am representing a paper entitled Post-Seismic Deformation of Lithosphere Caused by a Blind Strike-Slip Fault. This is our table of contents. First of all, summary. Aim of the present study is to determine the post-seismic deformation field for a two-layered model of Earth comprising of an elastically isotropic finite layer overlying a Maxwell viscoelastic half-space. A buried strike-slip fault of finite width is located in the layer at arbitrary dip angle. The co-seismic field is modeled by static solution, and the viscoelastic solution is found from the corresponding static solution by applying correspondence principle of linear viscoelasticity. The post-seismic field is obtained by subtracting elastic solution from the corresponding viscoelastic solution. The comparison of the co-seismic and post-seismic displacement field with epicentral distance are computed numerically for various relaxation time and for different dip angles. Introduction. Deformation during the three stages of earthquake cycle, namely interseismic, co-seismic, and post-seismic, exhibit different time characteristics. Our interseismic deformation, driven by tectonic plate movement, is slow and largely time independent. Post-seismic deformation is our time dependent, occurs due to the mechanism of stress release immediately after the earthquake. The creep process takes place in the deep ductile portion of the crust caused by viscoelastic stress relaxation in the mantle. Thus, post-seismic deformation is our delayed deformation of the Earth's surface due to viscoelastic stress release in the mantle or in the upper crust. Numerous studies are available in the literature on the deformation of a two-layered model of Earth due to strike-slip faulting. Several researchers like Rosenman and Singh, 1973 A and B, Singh and Rosenman 1974, Rundle and Jackson 1977, Rundle 1978, and several others have studied the viscoelastic deformation of a uniform half space or a layered medium for a strike-slip faulting by using correspondence principle of linear viscoelasticity or by relaxed rigidity method. Mayan Kuzni 1994, Singh and Rani 1994, Kato 2002, Kame et al 2000, and several other researchers. Now, mathematical formulation. In the Cartesian coordinate system, we adopt a two-dimensional approach in which the displacement vector u is exempted from x coordinate. Due to this hypothesis, the deformation is divided into two parts, plane strain and anti-plane strain case, which can be treated individually. Here we consider the anti-plane strain case only. For the anti-plane strain case, the displacement vector u is given by equation number 1, and under zero body forces, the equilibrium equations are given by equation number 2. This is the geometry of a very long strike-slip fault of finite width L inclined at an angle delta at depth h located in the layer overlying a Maxwell viscoelastic half space. Here we consider a two-layered composition of the Earth having a uniform elastically isotropic finite layer of thickness h, which symbolizes lithosphere, and which is overlying over a uniform half space which represents asthenosphere. The coordinate axis is taken at the surface of the layer with z-axis vertically downwards. Mu and mu naught be the rigidity of the layer and the half space. We assume the upper surface of the co-seismic deformation. Let us assume the upper surface of the elastic layer is traction free at pxz is our 0 at z is equals to 0. Also, we assume that the layer and the half space are welded along the interface z equals to h. The displacement and the stresses for the elastic layer welded with an elastically isotropic half space due to a vertical and a horizontal strike slip line dislocation has been obtained by Garg and Sharma 1992. Using these results, Singh and Rani 1994 obtained the deformation field induced by a long strike slip fault of finite width inclined at an angle delta situated in the layer. Rani and Singh 2005 extended their results for a long strike slip fault of finite width L inclined at an angle delta at depth h. Thus, the results for the layer are given by equation number 7, 8, and 9. And for the half space, results were given by equation number 10 to 12. Now, post-seismic deformation. Now we have to obtain the viscoelastic solution for a two-layered medium having an elastic layer over a Maxwell viscoelastic half space. We apply the correspondence principle for a viscoelastic material. Let the time-dependent dislocation source is given by a unit step function. B is our B naught HT, where B naught is our Magnitude of slip, ht is our Heaviside unit step function. For a Maxwell viscoelastic material, the constitutive equation is given by equation number 16, where epsilon is our shear strain, sigma is our shear stress, tau is our relaxation time. The Laplace transform of equation number 16 and 17 is given by equation number 18 and 19, where zeta is our Laplace transform variable and bar denotes our Laplace transform. In order to obtain viscoelastic solution in the Laplace transform domain, Flug 1975, we replace mu naught and b by mu naught bar and b bar in the equivalent elastic solution. From equation 7 to 12, it is observed that mu naught and b exist only in the expression of Mn, Nn, and Pn. Therefore, the viscoelastic solution in the Laplace transform domain is obtained from 7 to 12 on replacing Mn, Nn, and Pn by their respective Laplace transforms, which are given by equation number 21. Using the integral transform tables of Fridley 1954 to find the inverse Laplace transform of Mn bar, Nn bar, and Pn bar listed in table 1, we obtain the viscoelastic solution. The post-seismic solution is found by subtracting the elastic solution from the quasi-static solution. For the post-seismic deformation field, the solution for the layer is given by equation number 23 to 25, where phi mn and psi mn are given by equation number 26. The equations 23 to 25 give the post-seismic deformation field for the layer caused by a buried long inclined strike slip fault of finite width, buried at depth h. On putting h equals to 0, the post-seismic solution agrees with the identical results of Singh and Rani 1994. Numerical results. We examine the pattern of the co-seismic and post-seismic displacement of the layer given by equation number 7 to 9 and 23 to 25, assuming S1 is our 0 and S2 is our h by 2, which implies the fault length is our h by 2, caused by an infinite strike slip fault of finite width L, located at h equal to h by 4. We here consider the continental crust model, for which rho is our 2.22. The dimensionless quantities are defined for numerical computations by equation number 28. Now, figure 2.A exhibits the pattern of co-seismic displacement and post-seismic displacement with a horizontal distance y for a horizontal strike slip fault, and figure 2.B represents corresponds to a 45-degree dipping strike slip fault in which the post-seismic displacement u vanishes about y equal to 0.5 for all relaxation times. Figure 2C is for a vertical strike slip fault. For the vertical strike slip fault, co-seismic and post-seismic displacement are antisymmetric about the line y equals to 0. The co-seismic displacement has a significant variation near the fault as compared to the post-seismic displacement. Conclusions. Singh and Rani 1994 have obtained the co-seismic and post-seismic solution produced by a long dipping strike slip fault located in the layer welded with a viscoelastic half space. Also in their solution, when the dip angle is taken very small, the fault reaches near the surface of the layer. Hence, the results can't be applied for buried strike slip fault of small dip angle. In the current study, the upper edge of the fault is taken at depth explicitly and the solution is obtained for a buried fault. Hence, the effect of depth and dip angle can be studied independently. These are the references I have used, and thank you.
Okay, thank you, Deepika. Any question from the audience?
No, sir, no questions. Nice presentation, ma'am. Thank you.
Okay, so Deepika, thank you for the presentation.
No,
Thank you,
sir.
sir.
Saikut sir, I have one question.
Yeah, please.
Actually, Rani mentions some reference. She have taken some results, but I did not found any novelty of the present work. Got it?
Yes, sir.
I mean, you have mentioned some results.
Yes, sir.
what is your originality of the work? I mean, what you have done new in this paper, except blind or buried.
Sir, I have calculated it for the post-seismic deformation. Later, results were for co-seismic deformation.
Have you calculated or solved for viscoelastic subspace?
No, sir, for the layer.
For the layer, but which type of materials? Elastic or viscoelastic?
Sir, elastic.
So you did not solve for the viscoelastic aspects.
No, sir.
Got it. Okay.
हाँ जी sir.
Okay, Deepika, you may leave. You may leave the.
Thank you, sir.
Or if you want, you can stay. Just you mute yourself.
Okay.
Actually, please, other participants, please stay here.
Yeah.
Actually, so don't leave.
Yeah. So yeah. So I'm sorry. So you just mute yourself and stay.
Okay, sir.
So
Thank you.
let me call the next participant, which is Dr. I apologize if I pronounce it in incorrect way. So Dr. Jamie Kaben is here with us.
Yes, sir. Your pronunciation is correct. Thank you so much, sir.
Yeah. So may I request you to start your presentation?
Yes, sir. Just give me 1 minute. I'm going to share my presentation over here. Thank you, sir. Sir, my screen is visible? Hello?
Yes, it is visible.
Ji. Thank you so much, sir. So, first of all, Honorable Session Chairman of this conference, Dr. Saikat sir, and respected conveners of this conferences, Dr. Arpan Thara ma'am, Dr. Dipanjana Das ma'am, Dr. Sarosh Mandal sir, and all the organizing team. Thank you so much for giving me this opportunity to present my research paper in this conference. Myself, Dr. Jainika Ramesh, working as an assistant professor Adhyapak Sahayak in Department of Mathematics, Sir P.T. Sarvajini College of Science, Surat, Gujarat. Today I am going to give my presentation on a novel similarity transformation approach for studying MST effects in boundary layer flow of second grade viscoelastic fluid over a stretching sheet. So this will be the outline of my talk. I'm not going to read it. The abstract of my paper is, in this paper, a similarity solution is developed for the nonlinear partial differential equation that describe the two-dimensional laminar boundary layer flow of a viscoelastic second grade fluid past a stretching sheet. For this, I applied a newly formulated group dimensional analysis technique, which is applied here to find the similarity solutions. And this similarity transformation is reducing two variables into the one variable. I mean to say a non-linear partial differential equation is converted into the non-linear ordinary differential equation. So through this procedure, the original set of coupled nonlinear PDEs is transformed into a single third order nonlinear ordinary differential equation subject to the boundary conditions. Then after resulting similarity equations is solved also using an efficient numerical method to obtain accurate flow characteristics. The numerical results are also analyzed and the effects of various governing parameters on the velocity field and boundary layer behavior are thoroughly discussed. So for that, first of all, we have to understand what is similarity transformation. Actually, basically, we can say that in engineering problems, one has to include the boundary and initial values of the problem in similarity analysis. And this auxiliary condition must be transformed properly. Otherwise, no similarity solution is possible. Just I have mentioned that the method of transformation which convert nonlinear or highly nonlinear PDEs into nonlinear ODEs by reducing the number of variables by at least by one, which is called the similarity transformation. So let me here introduce this new group dimensional analysis technique. This method is basically established on basic physical dimensional conditions. And whatever solution we get, it is more realistic. And this method is actually based on quantitative grid analysis. So it is more suitable to solve system of nonlinear PDEs or system of higher order PDEs also. In this method, we can say that a system of dimensionless similarity variables such as Reynolds numbers and dimensionless coordinate variable, dimensionless velocity component, all these parameters are derived and determined through the analysis with the typical basic conservation equation. So for that here, in derivation of the dimensionless similarity variable, here stream function need to be defined, that is psi, and intermediate variables f of theta and its derivatives, these are also introduced. So the advantages of this method is more convenient for consideration and treatment of the variable physical properties, and it is more reliable or convenient for analysis and investigation of the two-dimensional velocity field. It is more convenient for satisfaction of the interfacial mass transfer matching conditions in the numerical calculation and for rigorous investigation of mass transfer for two-phase film flows with 3-point boundary value problem also. So this method is based on principle of the quantitative grid analysis, and in this method, we first of all it is necessary to define its analytical standards. A normal quantity grade that we regarded it as one, that is called a unit quantitative grade. Then after, a very small quantitative grade is regarded as a small delta. Even a very small quantitative grade is regarded as a delta square. So according to this principle of the quantitative grade analysis, such types of quantities are neglected in analysis so that we can easily find the dimensionless similarity variables or parameters. We can easily find the dimensionless coordinate variables and the dimensionless velocity component, etc. And hence we can easily get the similarity solution by using this new technique. So here we have defined one problem. This problem introduces laminar flow of a viscous, incompressible, electrically conducting second-grade fluid past a stretching sheet. And under the presence of transverse magnetic field, here equation number 1, that is represent over here the equation of motion of a fluid, that is continuity equation, and equation number 2, that is momentum equation, with the boundary condition which is given over here in equation number 3. Here we have written the sheet is moving in its own plane with a speed proportional to the distance from the origin, and here free stream velocity that you have taken A. So let us here first of all select the physical variables.
So please wrap it up in 1 minute, please.
GG. Okay, sir, fine. So as per the problem, we have selected this physical variables, that is n is equal to 7. Then after, as per the method says that then after we should find some basic dimensions also. So that is a basic dimension we have taken, that is r is equal to 4. And then after, as per the Buckingham pi theorem, we can say that n minus r, that is 7 minus 4 is 3. So according to Buckingham pi theorem, we need to find here dimensionless similarity parameters, that is called pi 1, pi 2 and pi 3. Then after we find here, as I told, similarity physical variables. As per the rule of Buckingham pi theorem, it will be r plus 1. So we get here 5 numbers of physical variable, which we are using to find those variables to find the dimensionless similarity parameters, which are given in equation number 6, 7 and 8. So as per this this rule of dimensionless, we have used these dimensionless units in our this system to find the 3 basic parameters, dimensionless parameters, pi 1, then pi 2, and then after pi 3. So then after we can easily find by using the concept of quantitative gradient analysis, we find the dimensionless coordinate variables over here, that is called eta, and this eta we found in equation number 15. And last we can find dimensionless velocity component also, which represents in x and y direction respectively in equation number 16, 17. So finally, we put all these values in our basic equations. We get here, and simplifying it, we get here this simple equations. Finally, in a complete similarity dimensionless equation, we get here the value of P and Q, that is P0 and Q is equal to minus 1 by 2. We put those these two values in our equations 16 and 7, then and the supposed equation 16 and 17, which I have shown you earlier, for the two-dimensional velocity components of boundary layer, we get here equation number 22 and 23. Similarly, we can find the application of the same technique over here by using the similarity transformation, by applying the similarity transformation in equation number 1 and 2. Ji sir. So this is the solution of the problem, and we get its numerical results. We get the velocity profile over here by using the different values of m and k. So finally, by using this method, it is successfully, we can employ this method to transform by a boundary layer equation governing the flow of an incompressible viscoelastic second-grade fluid past a stretching sheet. Similarity transformation and similarity equations are also derived systematically, and the velocity component u of eta and v of eta we can easily find, which is directly proportional to the related velocity component u and v. And finally, whatever equation we get, that equation is third order non-linear ordinary differential equation with boundary conditions, and similarity solutions are also derived here systematically. Finally, numerical solutions of this similarity equations, which is a third order non-linear ordinary differential equation, and it is derived in terms of a defect function. And by using this least square method, we to find the value of alpha, we use here defect function. Finally, we observe that the effect of the magnetic field is to reduce the velocity component parallel to the stretching surface, and also it is seen that the velocity decreases rapidly near the stretching sheet, and this rate is higher as k increases. So let me here acknowledge this presentation acknowledges the financial support received for the minor research project entitled A Study of Group Theoretic Approach to Solve Boundary Value Problems of Fluid Mechanics. So this project has been sanctioned under the UGC, Vinirabha South Gujarat University, Surat, Gujarat. So me gives a sincere appreciates the support which made the successful completion of the present research work. These are my some references. Thank you so much, sir.
Questions? Any question? Okay. So I don't think there is any question. So thank you for.
Thank you so much, sir. Thank you, sir.
So yeah, you stay here. You just mute yourself.
Sure, sir.
Okay. So the next I call Lakshmi Rani, Dr. Lakshmi Rani Basumatari.
Yes, sir. Yes, sir.
Yeah. So I request you to start your presentation. So, and please try to wrap by 5 to 6 minutes.
Sure, sir. Am I audible, sir?
Yeah, you are audible. Please start.
Okay. So today I'm going to present my research paper solution of Navier-Stokes equation for viscous fluid flow with one discrete heater. So main motivation of this work is there are so many literatures as I read, but the numerous scope for application in the present work in industrial and engineering. So this problem is regarding the 2D problem, steady incompressible fluid flow with natural pre-convective flow. The main objective is that we are considering a four-sided enclosure as a rectangular enclosure for this problem. So we are studying for 2D incompressible viscous fluid flow in rectangular enclosure. So we have used the method of affine finite differentiation scheme, and also we use the simple algorithm method by computing the programming code in C to get the numerical solutions of the flow variables. So there is so we are considering one symmetric diagram of this problem. So we are taking the discrete header and then three adiabatic velocities. So these are the governing equations. The first one is continuity, the second one is x momentum, y moment, third one is y momentum, and the fourth one is energy equations. And to normalize the these governing equations, we need to take the non-dimensional variables like that way along with the boundary conditions. For this problem, we need to study the staggered equations also. And for numerical discretization, we are using the affine finite differentiation scheme. And for numerical computation, we are taking a simple algorithm method. And so this is an iterative method. So we need to calculate by writing the program in C code. So for these results, we have found four passes: east, west, north, and south, like that way. For simple algorithm method, we need to use first the gas velocities UV and the pressure field and temperature also. So to calculate the momentum equation, we need to solve the discretized momentum equation. For pressure equation also, we need to pressure correction to solve the pressure correction equation. And for pressure and velocity correction, we are writing like that way. To solve the temperature discretization equation, and and the process will be going on until the solution gets converges. For the result, we are getting like u and v velocities along with the geometric horizontal direction of the geometric center. And over here, we are taking the Reynolds number 50, 100, 400, and 5000. And for velocity and the temperature controls like that way, and temperature curves are like that way. And we are taking one graph, numeric Nusselt number versus Reynolds number also. For results, we are getting the flow variables u, v, p, theta already been computed. The velocity, pressure, and temperature are depicted, and analyze the rectangular enclosure of the computed of the numerical solution. The average Nusselt number to higher until the geometric says. So this is the research preferences. Thank you.
Thank you for presenting. And now I ask questions from the audience, please. Okay, I don't think there is any question. So thank you for presenting. So
Thank
you
you, sir.
may mute yourself, please.
Yes, sir.
And next is Keshav Charan Parikh. Keshav. Keshav. No. So Keshav is not here. Let me call the next speaker, who is Suma.
Hi, yes, sir. Good afternoon, sir.
Yeah, Suma, may I request you to present?
Yes, sir.
Please continue.
Hello, Suma, your voice is not coming.
Suma,
Yes, sir.
so have you started?
Yes, okay, sir. Good afternoon, everyone. Myself is Suma. I am Research Scholar, Department of Mathematics, under the guidance of the Dr. Raghunath K.R. My title is Numerical Analysis of the Study MHD Flow in Saturated Porous Media under the Local Thermal Non-Equilibrium Conditions using the Bernoulli-Wavelet method. So next.
Hello, Suma, your screen is not visible. Please share again.
Okay, sir.
Okay, you can start now.
These are the outline of the presentations. First one is introductions, LTNE. Sorry, sir. First one is introductions. LTNE assumptions simplify the heat transfer
No, no,
modeling.
hello, Suma.
Yes, sir.
Yeah, so you have 26 slides and we all know about this thing. So you don't just read it. So go to your work.
Okay, sir. These are the introductions of the. These are the introductions. The most of the heat and mass
Yeah,
transfer.
so you don't have to read these things. Just go to your, yeah, you can start.
Second one is mathematical formulations. We have to consider the two-dimensional MHD flow through a saturated porous media under the LTNE conditions, where the stretching sheet derive the boundary layer motions. And for equation number 1 is a continuity equation, equation number 2 is a momentum equation, and equation number 3 and 4 are the temperature for fluid and solid. These are geometric in figure 1. MHD boundary layer flow over a stretching sheet embedded in a porous media subjected to the transverse magnetic field. These are the expressions of the governing equations, and equation number 5 is the boundary conditions. And equation number 6 are the similarity transformation. This similarity transform we have to apply the equation number 1 to 5. Then we get the equation number 7, 8, and 10. System we get the system of we have to solve the system of PD to system of OD. And these are the these are the expressions of the equation number 7 to 9. And equation number 10 is the boundary conditions. We have to apply the Bernoulli wavelet methods. These are the Bernoulli wavelet definitions. Then process of integrations of a matrix. We have to solve the up to psi of 1 comma 11. Then we integrate the above 10 bases in the respect of bases in eta, then limits from 0 to eta, then exhibit in the form of the linear combinations of the Bernoulli bases, then integrate these values. Then we get the matrices, 10 cross 10 matrices. Similarly, for various values of n, operational matrix of integrations can be generated. Then we have to solve the infinite boundary conditions to finite boundary conditions. We apply the equation number 7 to 10. We get the apply the modifications of the variables. We get the equation number 12 and equation number 13 and equation number 14. These are the, we have to convert the infinite boundary conditions to finite boundary conditions in equation number 15. Then we have next we apply the Bernoulli wavelength numerical methodology. In equation number 7, we have in equation number 12, we have to consider the higher order derivatives. In equation number, we have to consider the we have to assume and write it in equation number 16. B transpose is the Bernoulli wavelet unknown coefficients, and psi of omega is the Bernoulli wavelet known coefficients. Then we integrate equation number 16. We have to with respect to omega, the limits from 0 to omega, then we get the equation number 17. Then we have to again integrate in equation number 18. We get the equation number 19. Then we have to apply the boundary conditions in equation number 18 and 19. We get the equation number 20 and 21. Similarly, to apply the apply in a temperature, the temperature for fluid and solid, we get the equation number 25 and in equation number 30. To collocate the equations and determine the unknown coefficients, Bernoulli wavelet coefficients, we begin the substituting the Bernoulli wavelet expressions of the velocity, temperature for solid and fluid, transfer the governing equations. Next, we have to apply the collocation method to selecting the appropriate collocation points, and these within the intervals 0, 1. These collocation points are chosen based on the accurate requirements of the problem. Substitute expressions into the governing equations at these points held a system of nonlinear algebraic equations. This system represent the described the variations, the versions of the original boundary conditions, boundary value problems. The resulting algebraic system is then solved using the Newton-Raphson approaches to obtain the unknown coefficients, unknown Bernoulli wavelet coefficients. Once these coefficients are determined, they are used to reconstructed the numerical solutions of the velocity, temperature for fluid and solid in equation number 12 to up to equation number 14, subject to the boundary conditions, simplify in the equations 15. Then result and discussions, we have to convert by using the Bernoulli wavelet method of the order of our matrices in table 1. Then in table 2 is comparing of the wall temperature gradient result with these reference equation number 24 and 25, comparing the present values is in we get the very accurate values in Bernoulli. We apply the Bernoulli wavelet method. Then these are the graph for the velocity profile and temperature for fluid and solid. We plot the magnetic field. Then these are the conclusions. In this steady MHD fluid flow and through a saturated porous medium under the LTNE conditions was analyzed using the Bernoulli wavelet method, which demonstrated the stronger accuracy and convergence. The magnetic field suppresses fluid motions and reduces the fluid phase heat transfer through the Lorentz force, whereas the local inertial parameters enhance flow and increase the screen friction. Higher Prandtl numbers reduce the thermal diffusions, thinning both the temperature profiles, while stronger interface heat transfer drawn the system of towards the LTE behavior and phase specific thermal properties, particularly the property modify the conductive ratio and solid thermal diffusion ratio, identify the heat transfer in the solid phases. All the quantities include the screen friction for solid and fluid. Nusselt numbers were highly sensitive and magnetic inertial and conductive effects. These findings offer valuable insights in for the LTNE based applications such as thermal installations, geothermal system and energy store. These are my references, and thank you.
Thank you. Question from the audience? Any question from the audience, please? Okay, so I just have a small question.
Hello.
Yeah.
Okay, sir. Continue you. Then I will.
No, you
proceed.
please ask. You please ask.
Okay, okay. I have a question. I mean, the researcher used the Newton-Raphson method. So please tell us order of convergence of Newton-Raphson method, please.
So once again,
You have used Newton-Raphson method.
yes, sir.
Tell us order of convergence of Newton-Raphson method.
We convert this to Newton-Raphson method by using.
No. I am asking you order of convergence of Newton-Raphson method.
Yes, sir.
No. Actually, you are not getting my question. Okay. Pass.
Okay, so
Thank you, sir.
Suma, I just have a, can you explain me what is Nusselt number? In your study, you have used Nusselt number, right?
Yeah, yes, sir.
So what is it?
Mathematics background.
Do you know or it's okay?
Yes, sir. But slides is not.
No, do you know it like even without scrolling the slides?
So Nusselt number, we have to solve the velocity temperature profiles, sir.
Yeah, I'm asking what is its definition?
Sorry, sir. I'm forgetting.
Okay, thank you.
Thank you, sir.
So you may mute yourself, please. So let me call Pralisha Misra. Pralisha Misra,
Yes, sir.
are you here?
Yes, sir.
Yeah, so please start presentation. Please start your
Okay.
presentation.
Good afternoon, everyone. This is Pralisha Mishra from VSSUT, Sambalpur. I hope my screen is visible. Hello?
Yeah, it's visible.
Okay, thank you so much, sir. So, thank you for giving me this opportunity to share my work with you. So, I'm working on accelerated boundary layer flow, heat and mass transfer of a non-Newtonian fluid in a vertical porous matrix with variable suction and variable viscous effects. And I'm working under the supervision of Dr. Itishi Naik. And these are my outlines. Coming to the introduction. So this work involves the study of heat transfer and mass transfer along with the flow dynamics of a free convective fluid, and it has importance in understanding various natural and engineering processes. This intricate interplay of fluid motion, heat transfer, and porous medium interaction has garnered substantial attention due to its relevance in numerous industrial and environmental and scientific contexts. Applications include geophysical and atmospheric flows, lubrication, tribology, medical, biomedical and physiological flows, gas and oil reservoirs simulation, etc. So, coming to my work, the objectives are as follows: formulations, then determination of the equation governing the flow and supporting boundary conditions, uh, op- obtaining a numerical solution using the FDM technique, which is the finite difference method, and a comprehensive study on of the impact of various non-dimensional parameters has been done here. So coming to the major assumptions, here we have assume that the fluid is incompressible in viscous, and the variable viscosity of the fluid is temperature dependent, defined as with this relation, which shows an inverse relation with the temperature. And here gamma is the viscosity parameter, and also suction at the plate is treated as variable with time and given as v naught equal to 1 plus epsilon a e to the power mt, and whereas epsilon a is very small and treated as the suction parameter. So coming to my model, so this is my model. The first equation here uh, describes the motion, the second equation for the heat transfer, and the third equation for the mass transfer of the fluid. And this is the boundary conditions which is accelerated in nature, and these are my non-dimensional parameters which I have substituted to convert the dimensional governing equations into non-dimensional forms. So this is my non-dimensional governing equations along with the boundary conditions. Here we get the major parameters, that is the Grashof numbers, permeability, Prandtl numbers, external heat source, Schmidt number, and these are the suction velocities, and this is the variable viscosity parameter. So the solution process includes: first, the governing equations are converted into the non-dimensional equations using proper variables and parameters. And then I have used the Lazarin technique, which is the BTCS scheme, in which the discretization for time is in backwards, and for space we are using the central difference formula.
Yeah, please go to your solution.
Okay. Sir, actually I have not computed it, but I have shown the result and discussions for little time. Like we don't have that much time, so I have directly come to the results and discussion part. So here we have plotted for Grashof numbers. Both the figures, we can see that the flow is enhanced with increasing the Grashof numbers. Then comes the viscosity parameter, that is gamma. Here also, since it is inversely proportional, so with rise in Grashof number, it is rising the fluid velocity, and also with rise in the permeability of the porous media, the fluid gets enhanced. Then coming to the Prandtl number, here the velocity, and for temperature we have plotted, and in both the cases we can see a diminishing effect of Prandtl number on both the profiles. Similar effect can be seen for the Grashof numbers here. For the Schmidt number here. This is for concentration profiles. This one is for concentration and this one is for velocity. Another graph I have plotted for suction parameter. For suction parameter also, a diminishing effect is seen for both the profiles, that is fluid flow and temperature. So these were my major findings. I am currently working on this paper, not completely solved. So I am not computed for other parameters or combined effects I have not shown. So these are my major conclusions. That is augmentation in the Grashof number, mass Grashof number, permeability, and viscosity. The flow is tend to increase, and for Schmidt number and Prandtl number, there is a diminishing effect for concentration profiles with rise in the suction parameter and the Schmidt parameter. The concentration profile tends to decrease, whereas a rise is seen for the Prandtl number in temperature profiles. So that's all from my side. Thank you so much. Any questions? These are my references.
Questions from the audience? Questions? Okay, there is no question. I have a small question. Pralisha, what is phi and what is psi?
Sir, phi is for the concentration variable. We are solving for that concentration transfer. So I have taken that term as phi. And for psi, I have I have denoted that as the velocity profile.
Okay, and what is Grashof number? Can you explain in layman's like?
Yes, sir. The Grashof number is the dimensionless number in fluid dynamics and heat transfer, which is used to characterize the flow regime in natural convections, especially, and it is basically a ratio of buoyant forces due to heat transfer or concentration transfer to that of the viscous forces generated by the fluid flow.
Okay.
So with rise in the buoyant forces, since it is directly proportional to the Grashof numbers, we can have an enhanced flow for the fluid.
Okay, thank you very much.
Thank you, sir.
So you may mute yourself. So let me call my next speaker. Our next speaker is Shubhendu Maiti.
Yes, sir.
Yeah, so please start your presentation.
Okay, sir. Sir, my screen is visible.
Can you make it full screen?
Yes, sir. Yes, sir.
Yeah, please start your presentation.
Yes, sir. Yes. Myself, Subhendu Maiti, research scholar, Department of Mathematics, Swami Vivekananda University. My topic is bioconvective dihydrid ferronanofluid flow with heat and mass relaxation in a Darcy Fukushima porous medium. Introduction. Bioconvection arises from the collective upward swimming of motility microorganisms such as oxytactic and gyrotactic species. Their motion generate unstable density gradiently that trigger convection. This phenomena play role in biosensor, fuel cell, bioreactor, and the biomedical system. Caisson fluid in bioconvection. Caisson fluid representing shear tracing or wild stress behavior. Model biological fluid such a blood and interpreting gyrotactic microorganism in the Caisson nanofluid after affected in momentum and heat mass transfer.
Yeah, so I guess you are just studying from, you're just reading from your slide. So can you tell me what is the shear thinning or something you have written? Yeah, next page. Next slide. Yeah, something you have written, Cashon fluids representing shear thinning or yield stress. What is shear thinning?
Shear thinning rate of মানে rate of হচ্ছে thickness with
Yes.
the field.
Okay, you go ahead, please.
Nanofluid and ferrofluid. Nanofluid, nanoparticle is 0 to 100 nanometer. Fluid enhance the thermal properties, and ferrofluid magnetic nanofluid allow external magnetic field control, applying application in the ceiling, drug delivery, cancer therapy, and microfluid, and so on. Hybrid and trihybrid ferro nanofluid. Hybrid nanofluid combine the two types of nanoparticle, and trihybrid ferro nanofluid use the three Fe3O4, CO Fe2O4, and MnFe2O4, and these the multiple component fluid improve the heat, mass, and the momentum transfer under the magnetic dipole, and hence advance the cooling, bioconvective stability, and then the biomedical application. And Darcy-Futterman porous media. The flow in the porous media require the Darcy media model to account for the both the viscous and the inner side dark. And this is the critical to bioengineering and the thermal management. And activity energy effect. Activity energy influence the chemical reaction and nanoparticle diffusion in bioconvection. Higher activation energy can the suffer react the rate, but the enhance mass transference. And Catino-Castive model. Catino-Castive model, suitable temperature and concentration, and optimize heat and mass transference, reduce the entropy in a nanosystem. Research gap. Catino-Castive double fusion in a bioconvective trihybrid nanofluid flow past a stretching surface under the Darcy-Futterman drug and the magnetic dipole. The study transferred governing partial differential equation into the ordinary differential equation and the similarity variable, and solving using the MATLAB and BVP4C, and analytic effect of magnetic and activation and nanoparticle and parameters. Application finding the apply to the microelectronics, cooling, energy harvesting, bioreactor engineering, and solar thermal system, and so on. This is the mathematical model. Geometrically, the bubbles are porous media, and the nanoparticle are Fe3O4, CO Fe2O4, and Fe2O4, and microbes are used, and the water are 60%, and ethyl glycol 40%. And the mathematical formulation, governing equation. The equation of 1 is the continuity equation, du by dx plus dv by dy equal to 0, and the equation 2 represent the momentum equation, and equation 3 represent our energy equation, and equation 4 is represent the concentration equation, and equation 5 represent the microorganism equation. And the boundary condition are at y equal to 0, u equal to ax, v equal to v0, and so on. The equation 8 represent and y tends to infinity. The equation 9, equation 8 and 9 are represent the boundary condition, are use the similar value variable u is equal to x into f dash eta, v is equal to minus root over of a nu f into f of eta, এবং eta is equal to y into root over of a by nu f, and theta, phi and xi. The momentum equation are transformed. The governing momentum equation is transformed the equation 10, and the equation 11, the energy equation is transformed, and concentration equation, and microorganism equation, and the boundary condition. Non-dimensional parameter are used. P are the tail number, and B beta, beta star, beta double star, Casson fluid, porosity, inertia, and B1 হচ্ছে beta 1
Yeah, please
ferrohydrodynamic.
go to your conclusion. Results. Please go to your
The
results.
solution and the graphical representation, and conclusion. The increasing the Casson parameter reduce the flow velocity profit, and the larger porosity parameter increases restricted to the flow through the porous media, and increase the ferrohydrodynamic inertiity factor dimension velocity due to the magnetic restriction, and so on, and the reference, and thank you.
Questions? Yeah, Shubhendu. So can you go
Yes,
to
sir.
your first slide one time? Just first slide. Yeah, go open that PDF. Yeah, that is fine.
Sir.
Yeah, so I just have a simple question. Yeah, go to that slide.
Yeah.
Yeah, open that tab, that is fine.
Yes, sir.
Yeah, so first slide, yes. Okay, whatever it may be. So you have written something called microorganisms. What is that?
Microorganism means bacteria.
Okay. And what is this oxytactic and this gyrotactic species?
Oxytactics means হচ্ছে অক্সিজেনের রিফ্লেক্ট সঙ্গে যেটা থাকে, অক্সিজেন রিফ্লেক্ট করে।
Okay, and is it your work? Are you sure?
Yes, sir.
Okay, so how did you solve it? Did you use any numerical technique or any analytical technique? What?
Math lab and BB P4C.
Okay, so you have solved on your own.
Yes, sir.
Okay, good. Okay, I don't have any other question. So next is Dr. Yajuvindra Kumar.
Yes, sir, I am present.
Yeah, so may I request you to start presenting?
Okay, sure, sir, sure. Is it visible, sir?
It is visible. Please wrap it up within 5 or 6 minutes.
Okay, okay, sir. Good afternoon. I am going to present Haar wavelets in free axisymmetric vibration of annular nanoplate of variable profile. This is the geometry of the plate. We have an annular plate with inner radius R2 and outer radius R1. Thickness of the plate is varying, and we have considered linear variation in thickness. As we are considering the vibrations of nanoplates, so we need to use Iringian's non-local elasticity theory, and the constitutive equations can be written like this, where sigma is the stress, this is the Laplacian operator, these are the strains, this is the Poisson ratio, this is Young's modulus, and the relations between different quantities, these are bending moments mr and m theta. This is the rigidity of the plate in terms of Young's modulus, thickness, and Poisson ratio. Now, the governing equation of the motion of the plate is this equation, where W is the transverse displacement of the plate, Poisson ratio, Young's modulus, thickness, density, and circular frequency. This is the Laplacian operator. As we are considering axisymmetric vibrations of the plate, so generally we have r and theta, but due to axisymmetric vibrations, theta is absent. And this is the variation of thickness, linearly varying with the radius vector. This is the non-dimensional vector, and the equation becomes this. So this is fourth order ordinary differential equation with variable coefficients. And this one is the our frequency parameter that we have to calculate. Now, as we are using Haar wavelet method, so first we convert this. This is the our domain R2 upon R1 to 1. We have to convert this into 0 to 1 by using this transformation. So the equation 2 gets converted to equation 3, where B0, B1, B2, B3, B4 are defined like this. Now, we have considered two boundary conditions, whether the edge, outer or inner edge is clamped or simply supported. For clamped edges, we have two boundary conditions, either displacement is 0 or derivative of displacement is 0 at inner and outer edge. Similarly, for simply supported edges, we have these two boundary conditions at inner and outer edges. Now, as we use Haar wavelets, so this is the definition of a Haar wavelet. The Haar wavelet family is defined by equation 6, where S1, S2, S3 are defined like this. And here J is the maximal level of resolution. These are the collocation points. Now, according to this method, the highest order derivative is approximated in the terms of Haar wavelets. These are the unknown parameters, AI. Now, we differentiate equation 7 4 times. We get derivatives of lower orders and W like this. These are the unknown coefficients of integration. Now, we use these integration of coefficients using boundary conditions, and when inner and outer edges of the annular plate are clamped and clamped, C is used for clamped and S is used for simply supported, means inner and outer edges are clamped, both are clamped. So we calculate these two unknowns for this combination like this, and for CS the values of unknowns are these constant of integrations. For this combination, the values of constants of integration are these, and for SS means when both the edges are simply supported, the constants of integrations are calculated like this. So we discretize equation 3 and we get this eigenvalue problem. So we have to calculate this eigenvalue parameter. We take the modulus of this, and this is the characteristic equation. Now we have considered 4 combinations of boundary conditions, and the values of different type of parameter. This thickness parameter we have considered from -5.5 to 0.5. This is called the non-local parameter. Mu is called the non-local parameter, and value of these parameter are these. This is the basically this is the ratio of, this is called the aspect ratio, and m equal to basically this is not m, this is a typing mistake. This here is j equal to 7, means the level of resolution we have considered 7. And these are the graphs we have plotted between frequency parameter and thickness parameter. From here we see, as we increase the value of thickness parameter from -0.5 to 0.5, the value of frequency parameter in 3 modes. We have calculated first 3 natural frequencies. So in all the 3 modes, the value of frequency parameter increases for these values of parameters. This is for CS plate, for SC plate, for SS plate. Now, this graph shows variation of frequency parameter against aspect ratio. As we increase the value of aspect ratio from 0.1 to 0.5, the value of frequency increases in all the 3 modes. And these are the percentage variations. When we increase the value of R2 upon R1 from 0.01 to 0.5, means we get the increase of 196.9% between these 2 frequencies. For first mode, this for second mode, and this for third mode. For CS plate, for SC plate, for SS plate. Now this is the non-local parameter, and we can see that the value of frequency parameter decreases. This negative sign denotes that value of the frequency parameter is decreasing with increasing value of non-local parameter. And this value of non-local parameter equal to 0 shows that we for local boundary conditions, means this is simple plate, this is not nano plate. For CS plate, for SC plate, for SS plate, and these are the this is the comparison of frequencies in particular cases. For homogeneous isotropic uniform annular plate. These are the values by different researchers. For R2 upon R1 equal to 0.3 and Poisson ratio 0.3. And these are the values obtained using the Haar wavelet, means our approach. And these values are in good agreement with the values obtained by other methods by different researchers for these boundary conditions. These bold values. And conclusions: the frequency decreases as the value of aspect ratio increases, and with the aspect ratio, this is the non-local parameter, this is aspect ratio, frequency increases, and with the thickness parameter the frequency increases, and as the mode number increases, the value of frequency parameter also increases. And the frequency of isotropic annular plate can be obtained by putting this non-local parameter equal to 0. So these the desired frequency can be obtained by adjusting one or more parameters considered here. These are the references. Thank you.
Questions, please.
So if anyone...
Sir, for sake of my knowledge, I would like to ask one question. Sir, what is the non-local parameter?
Basically, non-local parameter is the ratio of, if this is visible, I tell. Basically, this is E0A upon R1. E0A upon R1. Somewhere it is defined. E0A upon R1.
All right.
Yes, E0A upon R1.
Okay, sir. What basically it interpret?
Basically, it interprets. It is used to define the nanomaterial. Basically,
All right. Okay.
yes.
Thank you, sir. Thank you, sir.
Any other question? Okay. So is there no question? So I request you to mute yourself.
Okay, okay, sir. Thank you, sir.
Thank you for the presentation, nonetheless. So let me call our last speaker, who is Vishaka A.
Yes, sir. Am I
Yeah.
audible?
So I request you to present.
Yes, sir. Is my screen visible, sir?
Yeah, it's now coming. Please present your slides.
Yes, sir. Is it visible?
Not yet. Yeah, now it is visible.
Okay. So, hello everyone. Good afternoon. My name is Vishakha Guzarkar, and today I am present the topic space-time fractional heat and carrier transport in semiconductor half spaces. And here I am using analytical approach. So these are my contents that I'm going through. First is the abstract of my research paper. So in this research paper, or in this research, we extend the classical photothermal model for an axisymmetric semiconductor half space by incorporating or by using space-time fractional derivative, in which we use capital time fractional derivative, capital derivative for a time fractional, and space fractional derivative for space variables. So this is the abstract of my research paper, in which for using analytical approach, I here use the integral transform technique, in which I use two transformation. One is the Hankel transformation, which is used to remove the space variable, and using Laplace transformation for the time variable. So next is the introduction. So basically, here we expand the results to predict the thermal and carrier transport process in a semiconductor half spaces. As we know that classical thermodynamic models or classical thermoelasticity gives the instantaneous responses, but fractional order theory gives the detailed responses or slow responses. So it increases the accuracy of the any experiment. So that's why we prefer the fractional order thermoelasticity theory to use here for our cylindrical semiconductor model. So this is the objective of our research paper, that this study is to develop and analyze the model for semiconductor half spaces by incorporating space-time fractional derivative. This is achieved by replacing the classical heat conduction equation by using fractional heat conduction equation, which involves capital as well as respace fractional differential operators. And we shows the result by using the cylindrical copper body, body. So these are the literature reviews that I am going through. The foundation of the fractional order theory is given by the Sherif, and further, many researchers do the work in thermoelasticity, out of which Raslan has solved thick plate problem with axisymmetric temperature distribution. He also solved a problem on half spaces fractional order generalized thermoelasticity due to the application of periodic heat source, which is studied by the Tripathi. Now my guide Varbhi, he considered the simply supported rectangular plate and determine its thermal stresses by using thermal bending moment with the help of time dependent fractional derivative, that he used only time fractional. Here we use time as well as space fractional derivative. Further, Filishtinsky solved the space-time fractional heat conduction equation and discussed its thermoelastic behavior, but for the one-dimensional space. Here we consider the two-dimensional space. In short, we consider three-dimensional space, but we use fractional derivative on only two-dimensional space only. That is r, that is the radius of a cylinder, and time variable. Next, Audi studied the theory of generalized micropolar thermoelastic diffusion under Lord Schulman model. And recently, Sherif investigated a fully coupled system of generalized thermoelasticity for semiconductor material or medium. Also, Tripathi studied the photothermal interaction in axisymmetric semiconductor half space. So these are the work done yet. Now this is the formulation of our problem by using space fractional derivative. Here we use beta as a space fractional parameter and alpha as a time fractional parameter. Here we consider the infinite solid cylinder, that's why the range of Z is varies from 0 to infinity, and we consider the hollow cylinder, that's why our radius is varies from B to C. These are the three boundary conditions which are given by the equation 2, 3 and 4. And these are the two initial conditions that is given by equation number 5 and equation number 6. So this is the main formulation of our problem. Next, to find the solution of this heat conduction problem, I already said we use integral transformation techniques, in which we use Hankel transformation and Laplace transformation. But Hankel transformation is used for the space-time fractional derivative. So that's why for Hankel transformation we prefer the finite Rees fractional derivative. And while using or while finding the while applying the Laplace transform derivative, in terms of fractional order, we use this definition which is given by the Capito. So by using both definitions and two transformation which is given by, so here is the first equation number 7 and 8 represent the definition of a Hankel transform and its inverse transform, and equation 9 and 10 represents the Fourier finite transform and its inverse. So this is the main definition that we are going to use to find the Laplace inverse, and this is the main problem while we face while finding the Laplace inverse. So while finding the Laplace inverse, we use here Metag-Labeler function, which also can be expressed in the form of exponential terms, but by using it in place of using exponential terms, we prefer to use Metag-Labeler function. Next, this is the final finding of our heat conduction equation, that is the temperature distribution, which is given by equation number 12. But while finding the potential functions, which is given by phi, and using this equation, we use this temperature function in this equation and also the boundary condition at r equal to b and r equal to c for t is greater than 0. So these are the stresses that we are finding. So here we calculate two stresses. One is the radial stress, which is given by sigma rr, and another is the angular stress, which is given by sigma theta theta. And here we find the phi, which is the displacement potential function given by this equation. To incorporate this result, we use graphical methods. So first figure shows the variation of a temperature for the fixed value of a beta, which is our time fractional term, which is fixed at 1.75. And for the different values of alpha, we got this graph for the temperature distribution. In figure number 2, for the radial stress, that is sigma RR, we again fix the time fractional parameter beta is equal to 1.75 and vary the space fractional operator, which is alpha, from 1, 1.5, 1.7 up to 2. So this is the graph given by radius stress against the radius. In third figure, we discuss angular stress, that is sigma theta theta, for again fixed value of a beta and different value of a alpha. So this graph shows the interactions between angular stress against the radius. And in final graph, we fix the value of a alpha and vary the value of a beta parameter, which is the time fractional parameter, for the temperature. So this is the temperature distribution graph for the different value of beta and a fixed value of alpha. Now, these are the for the fixed value of alpha and distinct value of beta. We also find the radius stress and angular stress as given in the figure. So the main finding of our research paper is we shows the dependency of a temperature and thermal stresses in axial and radial direction for distinct values of space-time fractional ordered parameter. So these are the symbols I am used here, and these are the references that I am going through while using this study. Thank you.
Okay, thank you. Open to audience, please. Questions? Question from the audience?
So please share your screen again. Yes, I have a query.
Yes.
Please open your present. Why are you taking transformation?
Sir, there are two types of techniques that we are going through to solve the heat conduction equation. One is variable separation method and another one is integral transformation technique. So for this, for the different kind of space
So
fractional data.
while I see you have taken Hankel transformation, right?
Yes.
So, so how you get in space-time domain when you use inverse and something, right?
Yeah, I using its inverse to back there in space variable, which is given by
So
here
is it
equation number
possible
8.
to invert analytically?
Yes, sir.
Okay, okay.
So
So
all the calculations are done by
analytical.
myself. Yes, sir.
Okay, okay. Thank you.
Yes, sir.
Okay, if there is no more questions, thank you, Vishaka again.
Thank you, sir.
Yeah, over to Dr. Saroj now.
So thank you, Dr. Shoikat Saab, for your nice chair for this session. And our validatory session will start soon. Actually, other group and group C presentation is going on. So validity session will start after ending the presentation at group C. So I will share the link for the validity session and please join at this link. So thank you to all. Thank you to Soikat. So let's see you.
Okay,
next.
thank you, Saroj. Thank you for inviting me. So yeah, so I'm leaving now. Is that fine?
Okay, you can leave, but I request you to join at the validity session if possible.
Okay, when it is? When is it?
After in the session of presentation at group C.
So in the same link only?
Link, actually it's morning's link.
Okay, so you WhatsApp me the link? Is that
Okay,
fine?
okay, I
Okay, so you WhatsApp me the link when I have to join. Okay,
okay,
then
okay.
I'll join. Okay.
Okay.
Okay, thank you.
Thank you so much, sir. Thank you.
Dear participants, you
Thank you, sir.
invalidatory session. I will share the link. Actually, link is WhatsApp group. I will share. Okay, thank you all.
Thank you, sir. Okay, sir.